Welcome to the Sleepy Brainist. Tonight, we're going deep into the shimmering silence of your own mind, a place where tiny electric whispers shape your thoughts, your dreams, and even your sense of self. Your neurons are talking in pulses, patterns, and ancient rhythms. But what are they saying, and how do they know what to say at all? If your brain could speak in words, what do you think it would say to you? Right now, in this moment. In the beginning, before thought, before memory, before identity, there was only a spark. Somewhere deep inside the developing folds of your brain, in the quiet stillness of the womb, a single cell reached out. It was not yet a neuron, not yet part of any system of meaning, but it was becoming. Driven by ancient instructions encoded in your DNA, this cell began its transformation, elongating like a root in fertile soil, stretching toward a distant signal, almost as if it knew it needed to connect. And then, it happened. A faint electrical impulse surged through its membrane. It was not yet thought, not yet emotion, but it was energy. And it was alive. This was the spark that starts it all. But what exactly is this spark? It begins with something almost too small to see. Charged atoms, called ions, dancing on either side of a neuron's membrane. Sodium and potassium, calcium and chloride, all balancing, shifting, held in place like coiled springs by tiny molecular gates. And when the conditions are just right, when a certain threshold is reached, these gates open, and the neuron releases its energy in a brief but powerful pulse of electricity. This is called an action potential, and it travels down the neuron's long arm, the axon, like lightning racing through a wire. But the journey doesn't end there. At the end of the axon, the pulse reaches a gap, a synapse, the space between neurons. Here, the language changes. Electrical signals are transformed into chemical messages as tiny sacs burst open, spilling neurotransmitters into the synaptic cleft. These messengers float across the gap and bind to special receptors on the next neuron, whispering instructions. Fire, inhibit, pay attention, forget. And just like that, the next neuron fires, and the next, and the next. This is how thoughts are born. This is how memories take shape. This is how you learned your first word, felt your first fear, dreamed your first dream. The first spark didn't just animate a single cell, it initiated a cascade, a chain reaction that led to the growth of trillions of connections in your brain, each one refined, strengthened, or pruned away through experience. Even now, as you lie in bed, listening to these words, countless neurons are firing in synchrony, carrying the meaning of this story from your ears to your mind's eye. And none of it would have been possible without that original, quiet ignition. The spark was not random. It was written into you, a blueprint passed down from countless generations, stretching back to the earliest nervous systems in ancient sea creatures, back to the first flickers of intelligence in the evolutionary tree of life. That same spark, revised, refined, reinterpreted, is still humming in your brain right now. You don't have to think about it. You don't have to will it into existence. Your neurons fire silently, without permission, painting your reality in real time. They allow you to hear a song and feel something. They allow you to remember a smell from childhood and be transported instantly to a forgotten moment. They let you wonder what it all means. And yet, the neurons themselves do not think. They do not feel. A single neuron knows nothing, but together, billions of them, speaking in patterns of sparks and silences, a mind emerges. The language of your neurons begins with that first flicker of electricity. It is a language older than words, a language that doesn't use letters or grammar, but timing, frequency, and connection. A neuron speaks not by what it sends, but when it sends it. The meaning is hidden in the rhythm. This rhythm is the secret music of your mind. Each moment, your neurons orchestrate everything: your breathing, your thoughts, your sense of time, your sense of self. Even as you drift into sleep, they continue their work, flashing silently, processing the day, filing memories, dreaming in abstract pulses. And still, it all began with that first single spark, a quiet ignition that said, simply, begin. The language of neurons is unlike any human language we've ever spoken, yet it is the one language that defines our entire existence. Beneath every emotion you feel, every memory you recall, and every word you understand, there is a hidden alphabet, an intricate code not made of letters or sounds, but of timing, rhythm, and patterns of electrical pulses. This secret alphabet is woven into the architecture of the brain. Each neuron, with its delicate branching arms, is both a receiver and a transmitter of information. But neurons do not talk to each other in complete sentences. Instead, they speak in spikes, rapid, all-or-nothing bursts of electricity called action potentials. These spikes are incredibly brief, lasting just a few milliseconds. But in the realm of the brain, that is enough, because it's not just that a neuron fires, it's when it fires and how often. Imagine an orchestra where each neuron is an instrument. Some play quick, staccato bursts. Others hold long, slow, resonant tones. Alone, each instrument might sound meaningless. But when many fire together, in harmony or in complex interplay, a message is created, a feeling, a thought, a memory. The timing between each spike is one of the key elements of the neuronal alphabet. Some neurons fire rapidly, in rhythmic sequences, like the steady beat of a drum. Others fire sporadically, only in response to specific triggers, like a distant chime signaling a change. The space between the spikes is as important as the spikes themselves. A neuron that fires 100 times in a second is saying something very different than one that fires 5 times in that same span. But there's more than rhythm. There's also location. Where in the brain a signal originates changes its meaning entirely. A pulse in the visual cortex carries information about light and shape. That same pattern in the auditory cortex may correspond to a melody or a familiar voice. The alphabet is not universal. It's localized, like regional dialects. Each area of the brain develops its own codebook, adapted to its specific function, yet always able to work with the rest. To understand this language is to begin to grasp how we perceive reality. Take, for example, the simple act of seeing a red apple. Light enters your eye, strikes your retina, and is converted into signals, bursts of information that travel through the optic nerve to the brain. There, in the visual cortex, specialized neurons decode the shape, the color, the motion. Other regions, like those associated with memory, light up in response. You remember the taste of apples. Maybe you recall your grandmother's orchard. The neurons responsible for emotion might stir if that memory is sweet or painful. All of this happens in a matter of milliseconds, a whole sentence of neuronal language unfolding in silence. But no single neuron carries the entire message. Each contributes just a letter, a pulse, a piece of the whole. Meaning arises only when many neurons fire together in specific spatial and temporal patterns. These combinations form the brain's alphabet, not static, not written, but emergent, unfolding anew each time you think, feel, or sense something. There is even a form of syntax. Neurons organize their signals in particular sequences, depending on what is being communicated. In some cases, the same neurons may fire in different orders to mean entirely different things, just as the same letters can form different words depending on how they're arranged. Scientists call this neural coding, and it remains one of the most mysterious frontiers in neuroscience. We can see the spikes, we can measure their timing, but what they mean is still, in many ways, a puzzle. Even more fascinating is the idea that this alphabet can evolve. The brain is plastic, meaning it can change and adapt over time. When you learn something new, when you practice a skill, or even when you change your habits, the structure of your brain subtly shifts. Synapses are strengthened or weakened. New connections form. Old ones are trimmed away. The alphabet itself rewrites its rules to accommodate your changing life. This is how the brain stores new information, by literally reshaping the way it speaks to itself. And yet, despite the complexity, this alphabet never speaks in chaos. It is astonishingly organized. Even during rest or sleep, your neurons continue to fire in meaningful rhythms. Slow waves during deep sleep, rapid bursts during dreams. These patterns are thought to be essential for memory consolidation and emotional processing. The brain never truly goes silent. It is always whispering, always communicating, always remembering. What's even more beautiful is that this language is universal, across humans, across animals, even in the most ancient creatures with rudimentary nervous systems. The specific messages may differ, but the core mechanism, spikes, synapses, rhythms, remains. From the hummingbird navigating wind currents to the octopus solving puzzles in the deep sea, the same alphabet is at work. It is a language not of culture, not of words, but of life itself. And as you lie there, calm, quiet, drifting deeper into stillness, this language is still speaking inside you. You may not hear it, but your brain is translating the world into pulses of light, sound, sensation, and thought. Each neuron fires its part of the message, contributing to a beautiful, silent conversation that never ends. Imagine a vast forest hidden inside your skull. In this forest, there are no birds, no winds, no footsteps, only the soft flicker of energy passing from tree to tree, root to root, leaf to leaf. These trees are your neurons, tiny, branching, pulsing cells that form the dense, living network of your brain. And in this forest, no tree stands alone. Each one is part of an intricate system of communication. These are the messengers of the mind. A single human brain contains around 86 billion neurons. That number is almost unimaginable. If each neuron were a person, they would populate a dozen Earths. And yet, within your head, they all coexist in a delicate balance, exchanging information constantly, quietly, tirelessly. Neurons are not only the most specialized cells in your body, they are also the most talkative. They exist to send and receive messages, relaying signals that shape your experience of the world from moment to moment. Every thought you've ever had, every emotion you've ever felt began with these tiny messengers. But what does it mean to be a messenger in the brain? Each neuron is shaped like a strange tree with three main parts: the cell body, the dendrites, and the axon. The cell body holds the nucleus, the heart of the neuron, where the cell's essential processes are managed. The dendrites are like thousands of fine, delicate branches, fanning out like the limbs of an old oak tree. These receive incoming messages from other neurons. The axon, on the other hand, is the long, slender arm that extends outward, sometimes stretching a meter or more in the case of neurons that travel down the spinal cord. The axon is the neuron's voice, its way of sending messages forward. The process begins when a neuron receives a signal through its dendrites. That signal can come from another neuron or from a sensory input: light, sound, touch, taste, smell. If the incoming signals are strong enough, the neuron decides to pass the message on. This decision is made at the axon hillock, a tiny but powerful decision-making zone at the base of the axon. If the input exceeds a certain threshold, the neuron generates an electrical impulse, a quick burst of voltage known as an action potential. This electrical impulse then travels down the axon, like a wave of fire along a fuse. The axon is insulated by a substance called myelin, which speeds up the signal. In fact, the message can travel faster than 250 miles per hour. It's a rapid, efficient delivery system, messages flying from neuron to neuron faster than you can blink. But when the impulse reaches the end of the axon, it encounters a challenge, a tiny gap between itself and the next neuron. This is the synapse. The neuron cannot send electricity across this gap, so it changes tactics. The electrical signal is transformed into a chemical one. Neurotransmitters, chemical messengers, are released from sacs at the end of the axon and float across the synaptic cleft. When they reach the next neuron, they bind to receptors on its dendrites, triggering a new electrical impulse. And so, the message continues. This is the essence of neuronal communication. Electricity becomes chemistry, and then chemistry becomes electricity again, over and over, millions of times each second. Some messages are simple, like telling a muscle to contract. Others are incredibly complex, involving networks of thousands or millions of neurons working in concert. For example, when you recognize a friend's face, signals must pass through multiple regions of your brain: visual cortex, memory centers, emotional processing areas. Each region handles a piece of the puzzle, and neurons are the couriers delivering these pieces in real time. And they are astonishingly efficient. A single neuron can form thousands of synapses, allowing it to communicate with a vast number of other neurons. This is how thoughts are not isolated events, but dynamic, interconnected patterns. The brain doesn't store ideas in single neurons, like files in a cabinet. Instead, it weaves them into webs of activity, constellations of firing neurons that light up together whenever that idea returns. What makes this even more extraordinary is that neurons are selective in what they say. Not every signal gets passed along. Some are inhibited, silenced, told to stop. The brain relies just as much on stopping signals as it does on starting ones. Like any good conversation, it depends on timing, listening, knowing when to speak and when to pause. This balance is what allows you to focus, to ignore distractions, to regulate your emotions, and to respond to the world in meaningful ways. Even as you lie still in a darkened room, your neurons continue their work. They're processing the sound of this voice, They're adjusting the rhythm of your heartbeat. They're guiding your breath, coordinating the memory of what was said moments ago with the emotion it brings, and maybe even letting you drift slowly into a more relaxed, peaceful state. The messengers of the mind never sleep. They are always at work, even when you are not. During sleep, neurons don't stop. They shift their focus. They replay patterns from the day, strengthen important memories, and gently sweep away unnecessary clutter. It is a time of recalibration, of dreaming, of silent organization. Neurons have no awareness. They don't know what they're doing, but their collective behavior gives rise to awareness itself. When billions of neurons fire in just the right patterns, consciousness emerges. The you that is thinking, wondering, drifting, that sense of being, is not separate from the neurons. It is their chorus. Each one is a simple messenger, passing along tiny packets of information, but together, they are the architects of your reality. You are, in a very real sense, a message made of messages. Your memories, your identity, your sense of time, all composed of neuronal signals flowing in endless harmony. And now, as you drift towards sleep, the messengers continue to speak, not in words, but in pulses, not in sentences, but in rhythms. Your brain, vast and silent, continues its conversation with itself, and you are gently carried along by the language of the mind. There is a language so quiet, so delicate, that it cannot be heard, only felt in the subtle rhythms of thought, memory, and emotion. It is a language spoken not with mouths, but with pulses of electricity. It flickers through you moment by moment in absolute silence. These are the electric whispers in the dark, the hidden signals that carry your mind's most intimate secrets. Every second, countless tiny electrical surges ripple across your brain. These surges, known as action potentials, travel along neurons like messages in a bottle, crossing vast networks of connections in mere milliseconds. They do not shout, they do not announce themselves, and yet they shape everything, from your quietest thought to your most intense emotion. You have never seen these sparks, and you never will, but they are there. They are the reason you know the difference between a dream and a memory. They are the reason you can recall a face, hear a song in your head, or imagine a future that hasn't happened yet. These electrical pulses are your brain's way of thinking, of remembering, of becoming. They are the lights that flicker behind the curtain of your consciousness, and they are always in motion. Even when you sit still, even when you sleep, even when you think your mind is blank. Beneath the surface of your awareness, billions of neurons are exchanging signals, like fireflies blinking in a vast, shadowed meadow. Some neurons send their messages rapidly, hundreds of times per second, while others are more restrained, firing in slow, steady rhythms. The variety of these electrical patterns is what gives rise to the complexity of the mind. Just as music needs both fast and slow notes, loud and soft, your brain depends on variation to create meaning. The darkness in which these whispers take place is not physical darkness, but a kind of quiet mystery. The brain is encased in the skull, protected from light, sound, and the outside world. It lives in perpetual shadow, relying entirely on the messages brought in by your senses. Yet from within this darkness, it generates all the light you have ever known. The brightness of memory, the flash of insight, the warm glow of love. And so these whispers become more than signals. They become the very texture of your life. But how does something so faint, a tiny voltage change, a microscopic spark, become something as rich as a memory or as real as a feeling? It begins with organization. Neurons do not fire at random. They are arranged in circuits, like musical notes arranged into a symphony. Some circuits are ancient, inherited from millions of years of evolution, the ones that help you breathe, stay balanced, and survive danger. Others are newer, more personal, formed by your unique experiences, shaped by the people you've met, the stories you've heard, the joys and pains you've lived through. Each of these circuits has a particular pattern, a sequence of activations that gives rise to specific experiences. When you see a familiar face, a certain pattern lights up in your visual cortex. When you remember a comforting song, another network in your auditory cortex and memory centers comes alive. These electric whispers flow through the specific pathways they've used before, like well-trodden trails through a forest. The more often you revisit a trail, the stronger it becomes. This is the essence of learning and memory. Neurons that fire together, wire together. Their electrical conversations become more efficient, more synchronized, more fluid. It's why repetition helps you remember. It's why a scent from childhood can bring back a flood of emotion. The whispers grow louder, not in volume, but in clarity. There is also a kind of timing, a deeper rhythm, almost musical in nature. Your brain has its own electrical beat, known as brain waves. These waves, measured in frequencies like alpha, theta, and delta, represent the overall tempo of your neural activity. When you're relaxed and awake, your brain produces gentle alpha waves. When you drift into sleep, slower theta and delta waves take over. These waves are not whispers themselves, but the stage upon which the whispers are performed. They set the mood, the pace, the readiness of your brain to perceive or dream. Even more beautifully, your brain is capable of creating silence within itself, purposeful quiet. It is in these moments of reduced activity, these lulls in the electrical chatter, that you often find clarity, insight, or peace. In the deep stillness of meditation, or in the calm just before sleep, your neurons slow their rhythm. The whispers soften, making space for something new to emerge. Sometimes, silence is part of the message, and yet, these whispers are not infallible. Sometimes, the signals become too loud, too disorganized. This can lead to confusion, anxiety, even mental illness. The balance of excitation and inhibition, of sending and receiving, is delicate. A single misfire can ripple outward, affecting entire networks. Still, even in the chaos, the brain tries to restore harmony. It is always listening for the whisper beneath the noise. In the deepest parts of the night, when your body is resting and your conscious mind has faded, the electrical whispers continue. They replay fragments of your day, stitching them together into dreams. They file away moments, solidify knowledge, and clear out the unnecessary clutter. This is why sleep is sacred for the brain, a time when its quiet language becomes most profound. And so, while the world sleeps around you, your neurons whisper their secrets. You may never hear them, but you feel them, in the memories that come uninvited, in the flashes of understanding, in the strange comfort of a dream you can't explain. These electric whispers are always there, beneath your thoughts, your identity, your awareness. They are the quiet current that carries you from one moment to the next. And tonight, As your own brain slows its rhythm and slips into rest, those whispers will keep speaking. Gentle, electric, eternal, lighting the dark in perfect silence. Before a thought can be formed, before a memory can be recalled, something must happen. Something subtle, yet profoundly important. A signal must travel. A bridge must be built. A connection must be made. In the mysterious, ever-changing landscape of the brain, this is the first connection, the birth of a thought. But it does not happen in isolation. It begins, always, with sensation. A flicker of light hits the retina. A soft sound vibrates through the air. The scent of something familiar wafts through the air and reaches the delicate structures in the nose. These sensory impressions are not yet thoughts. They are raw signals, fragments of the external world entering your internal world. They journey along specialized pathways into the brain where neurons wait, poised, sensitive, ready. And if the signal is strong enough, or meaningful enough, or familiar enough, something extraordinary occurs. Neurons begin to fire together, not randomly, but in patterns. One neuron activates another, then another, and another. A small network ignites. This chain reaction is not just electrical. It is the transformation of experience into meaning. The first connection is the moment a sensation becomes a perception, the instant when a blur becomes a face, when a vibration becomes a voice, when a thought begins to take form, fragile, brief, like a mist rising from still water. At the heart of this process lies the synapse, the tiny gap between neurons. Synapses are where the real magic happens. When a neuron fires, it sends its message to the end of its axon, where it meets the synapse. There, neurotransmitters are released into the gap, drifting across to the next neuron, binding to receptors. These receptors are like locks, and the neurotransmitters are the keys. If enough keys fit, if enough receptors open, the receiving neuron fires too. This process, the leap across the synapse, is the essential spark of communication. And it is here, in this silent electrical and chemical exchange, that a thought is born. Not a grand, complex idea, not yet. The first thought is simple, elemental. Something is here. It could be the awareness of warmth on your skin, the recognition of a sound, the sense that someone is near. It begins with presence, with attention, with a signal strong enough to rise above the background noise. From here, the thought grows. The initial signal travels onward, pulling more neurons into its pattern. The visual cortex may become active, interpreting shapes and colors. The limbic system might respond with emotion, assigning significance. This is beautiful. This is frightening. This is familiar. The hippocampus, the keeper of memory, searches its archives. Have we seen this before? What does it mean? And finally, the prefrontal cortex lights up. This is the seat of higher thought, the place where reflection, judgment, and imagination live. Here, the brain can hold the signal in working memory, turn it over, ask questions. Here, a raw perception becomes something more, a decision, an idea, a plan. But none of this could happen without the first connection, without the initial spark between one neuron and the next. And this is not just the story of one moment. This is the story of every moment you've ever experienced. Each time you learn something new, a word, a melody, a face. Your brain is making connections that didn't exist before. Each one is small. Alone, it means very little. But together, over time, they form networks, patterns, pathways. Your thoughts are not stored in single places. They are stored in relationships, in the connections between neurons. And what's even more remarkable is that these connections can be shaped, strengthened, transformed. This is the principle of neuroplasticity, the brain's extraordinary ability to change, to adapt, to grow. Each time you revisit a thought, practice a skill, or reflect on an idea, the connections between the relevant neurons become stronger, more efficient, more likely to fire again. It's like carving a path through the forest. The more often you walk it, the clearer it becomes. This is how habits are formed, how memories are solidified, how the brain learns what matters. And yet, for all its power, the first connection is delicate. Neurons are choosy. They require the right balance of signals to fire. Too much inhibition, and the signal fades. Too much stimulation, and the system can become overwhelmed. There is a sweet spot, a perfect harmony, in which new connections form. In infants, this process is happening constantly. The developing brain is flooded with new information, and the neurons are hungry to connect. That's why childhood is such a fertile time for learning. The brain is flexible, responsive, open. But this capacity never disappears. Even in adulthood, your brain is capable of change, of forming new connections. Every time you have a new insight, every time you feel something deeply, every time you notice a pattern you hadn't seen before, a new connection is being born. Even now, as you read these words, as you hear these thoughts in your mind's voice, your brain is making subtle shifts. Certain neurons are firing that didn't fire before. New circuits may be forming. And somewhere in that activity, a new idea might be born. Gentle, shimmering, just out of reach. The first connection is never the last. It is a doorway, a beginning. The first step in the long, silent dance of your mind. And it all happens in the quiet, in the dark, in the soft electric whisper of neurons meeting for the first time. A thought begins as a flicker becomes a pattern, and a pattern becomes you. It begins quietly. A single neuron rests in a sea of possibility, waiting for the world to touch it. It does not know what will arrive. A flash of light, a sudden sound, a gentle thought. But it waits, suspended in silence, until something crosses its threshold. Then it happens. A whisper of charge builds at the edges of its membrane. Ions shift, channels open, and with a sudden decisive surge, the neuron sends a signal racing down its long axon. This is not a slow process. It is swift, sharp, and full of intent. It is the moment a neuron says hello. But this greeting is unlike any word, any spoken phrase, any familiar gesture. It is a pulse of electricity, no louder than a few millivolts, and it lasts less than 1,000th of a second. And yet, in the world of the brain, this is everything. This tiny electrical burst is called an action potential, the basic unit of communication between neurons. It is how your brain speaks to itself, how it transmits meaning, movement, memory, and emotion. It is the elemental wave, the primal voice, the neuron's way of saying something is here. To reach this moment, the neuron must pass a critical threshold. It is not enough for a signal to merely arrive. It must be strong enough, persuasive enough, insistent enough to trigger a response. The neuron listens carefully, balancing inputs from thousands of neighboring neurons. Some signals urge it to speak. Others tell it to stay silent. This balance is delicate. It ensures that your brain is not a chaotic storm of electrical noise, but a coordinated dance of meaningful communication. When the signal reaches that tipping point, the neuron unleashes its potential. Sodium ions rush in, potassium ions flood out, and a wave of depolarization travels rapidly down the axon, like fire racing through a fuse. This is the moment of transmission. But the axon is not a straight wire. It is wrapped in segments of insulating material called myelin, which acts like the coating on an electrical cable. This insulation doesn't slow the signal, it accelerates it. The action potential leaps from one uninsulated gap to the next in a process called saltatory conduction. It jumps, skips, dances its way toward the axon terminal at speeds up to 250 miles per hour. When it reaches the end of its journey, the signal arrives at the axon terminal, the narrow tip of the neuron, but it cannot jump directly into the next neuron. There is a tiny gap in the way, a microscopic cleft, no wider than a strand of DNA. This is the synapse, the pause between messages, the quiet between notes. And so, the neuron must change its voice. It must translate electrical energy into chemistry. At the axon terminal, the electrical pulse triggers small vesicles, tiny bubbles of neurotransmitters, to move toward the membrane. These vesicles merge with the boundary of the neuron and release their contents into the synaptic cleft. Like messengers released into a stream, these neurotransmitters drift across the gap and bind to receptors on the next neuron's dendrites. If the message is strong enough, it will be heard. The next neuron, sensing the chemical signal, opens its own channels, adjusts its own balance, and, if the stars align, fires in return. A new action potential is born. Another hello is sent, and the message continues on its way. This entire process, from initial threshold to final transmission, occurs in less time than it takes to blink, and it happens over and over again, billions of times every second, across trillions of synapses in your brain. Each one is a whisper. Each one is a greeting. Each one is a neuron saying, "I've received the signal, I am alive, I am passing it on." But the message doesn't always mean hello. Sometimes it means pause. Sometimes it means remember. Sometimes it means run, laugh, listen, sleep. The meaning depends on the pathway, the context, the timing, the pattern. The same neuron might say hello in one moment and stay silent in the next. It is not just about whether a neuron fires, but when, how often, and in concert with whom. This is what makes the brain so extraordinary. It is not just a machine. It is a living network of relationships. Neurons are not isolated switches. They are participants in a conversation that spans your entire life. They shape your ability to speak, to learn, to love, to wonder. And this conversation is not fixed. It is always evolving. When you learn something new, the way neurons greet one another changes. New synapses form, old ones strengthen or fade. A neuron might begin to say hello more quickly, or hold its greeting longer, or wait for a different cue. Even silence can be a kind of greeting, a decision to listen instead of speak. And this moment, the moment a neuron fires for the first time, happens inside you every time you think a thought, feel an emotion, take a breath, or close your eyes to dream. It is happening now. As you lie still, resting in the quiet space of your own mind, countless neurons are saying hello to one another. Some are waking memories, others are processing sound. Some are slowing your heartbeat, others are preparing you for sleep. All of them, together, are engaged in a vast, gentle dialogue that defines your inner world. So much of what you are, your personality, your dreams, your creativity, begins with this simple greeting: a pulse, a leap, a hello in the dark. It is the brain's most basic gesture of awareness, its invitation to connection, its first word in the long, ongoing sentence of you. Deep within the labyrinth of your brain, there is a constant flicker of activity, not chaotic, not aimless, but purposeful. This activity is not made of words or images, but of tiny surges of energy, moving from cell to cell with astonishing speed. These are the synapses, the sacred meeting points between neurons. And what happens here is as close to magic as biology gets. To understand the gentle fire of synapses is to understand how your mind lights up with meaning. At the core of every thought, emotion, memory, and action lies a signal that must be passed on. But neurons are not fused together. They don't touch. Instead, there is always a microscopic gap between them, an impossibly narrow space known as the synaptic cleft. And yet, it is across this gap that the most important messages of your life have traveled. When a neuron fires, sending its electrical signal down the axon, that signal doesn't leap across the gap on its own. It comes to a stop at the synapse, like a traveler reaching the edge of a river. But this river is only a few nanometers wide, a space so small that even a light wave would hesitate. Here, at the edge, the electrical message must transform. Vesicles, tiny sacs filled with neurotransmitters, wait just beneath the surface. Triggered by the arrival of the signal, they move swiftly to the membrane of the neuron, fuse with it, and spill their contents into the synaptic cleft. These neurotransmitters are chemicals, yes, but in the context of the brain, they are something more. They are the vocabulary of neurons, the tone, the mood, the fire behind every signal. They do not float aimlessly. They know where to go. On the other side of the gap, on the receiving neuron's dendrites, are special proteins, receptors, shaped precisely to fit specific neurotransmitters. When a molecule locks into place, it opens a channel. Ions rush in. The electrical balance shifts. And if the signal is strong enough, a new action potential is born in the next neuron. From electricity to chemistry, and back again to electricity. This is the beautiful cycle of the synapse. But not all synapses are the same. Some are excitatory. They encourage the next neuron to fire, passing the message along like a torch. Others are inhibitory. They silence the signal, telling the next neuron to pause, to resist, to reflect. This balance between excitation and inhibition is delicate, crucial, and constantly adjusted. Too much excitation, and the brain becomes overstimulated, frantic, anxious, chaotic. Too much inhibition, and the signal falters, becomes lost, muted, numb. The gentle fire of synapses is the harmony between these two forces, not too loud, not too quiet, just enough to think, to feel, to be. And while the spark that ignites a synapse is tiny, the consequences can be enormous. A single synaptic event may trigger the recollection of a childhood memory. Another may guide your hand to reach for a cup. A cascade of them can lift you into joy or plunge you into sorrow. There is no separation between brain and mind here, only energy, flowing in precise, elegant patterns. In each of your thoughts, thousands, even millions, of synapses are lighting up in sequence. Some are newly formed, fresh trails in the neural landscape. Others are well-worn, reinforced through years of repetition. These familiar pathways are what make habits feel natural, skills feel automatic, and memories feel personal. And yet, even the most ancient synapse is capable of change. This is where the true gentleness of the fire lies, in its flexibility. Synapses are not fixed like wires in a machine. They are plastic, adaptable, and responsive. With each experience, your brain rewrites itself. Synaptic connections strengthen when used and weaken when neglected. This is called synaptic plasticity, the physical basis of learning. When you study a new language, practice a new movement, or reflect on an idea, you are literally reshaping the synaptic connections in your brain. You are tending the fire. You are coaxing it to burn in new directions. And this fire never truly goes out. Even in sleep, your synapses are at work. They prune what is no longer needed, consolidate what is important, and reorganize patterns of thought beneath your awareness. The dreams you have, the memories that emerge, the strange logic of the sleeping mind, all are born of synaptic activity. The fire burns softer, but never stops. Even now, as you rest, as your body relaxes and your breath deepens, the synapses in your brain continue to spark in gentle rhythm. They are interpreting these words, mapping them onto old memories, attaching them to emotions, filing them away for later. In this quiet dance, the boundaries between mind and matter dissolve. What you feel is what you fire. What you remember is what you've lit up before. What you imagine is the synapse creating something new, a fire where there was none. Each synapse is a small act of trust, one neuron reaching out to another, saying, "I have something to share." And when that message is received, something invisible becomes real. It is easy to forget that your brain is made of fire, not the fire that burns, but the fire that builds. A fire of intention, a fire of communication, a fire that whispers instead of roars. The gentle fire of synapses is not dramatic. It does not demand your attention. It simply continues, moment after moment, to light the path of your mind, illuminating your past, powering your present, and creating the future you have yet to imagine. And as you drift closer to sleep, this quiet flame burns on, steady, soft, eternal, the pulse of being, deep within. Imagine standing in a forest where every tree is reaching out, listening. Their branches stretch not only upward, but outward and inward, weaving a quiet web of attention. They don't shout, they don't move, but they listen. With absolute precision. This is the world of dendrites. Dendrites are the quiet arms of the neuron. Their name comes from the Greek word dendron, meaning tree, and their shape mirrors this beautifully. Thousands of fine branching tendrils radiating out from the neuron's cell body, like roots seeking nourishment, like antennae waiting for a signal. But what they are truly listening for is connection. They are the receivers in the great conversation of the brain. Every second, your dendrites are bathed in the whispers of other neurons. From trillions of synapses, tiny chemical messages drift toward them, messengers of thought, sensation, memory, and feeling. The dendrites don't create these signals. They don't fire them. They listen. They interpret. They decide whether a message is strong enough to be passed on. And their listening is not passive. It is complex, deliberate, and responsive. Each dendrite contains hundreds or even thousands of small structures called dendritic spines, little protrusions shaped like mushrooms, buttons, or filaments. These are the precise places where synapses occur. Each spine is a landing site, a meeting point, a doorway. When neurotransmitters released by another neuron float across the synapse, they bind to receptors on these spines, and the message is received. But the dendrite does not always respond the same way. Some messages are excitatory, encouraging the neuron to fire. Others are inhibitory, telling it to stay silent. The dendrite integrates all of these signals across time and space. Dozens, hundreds, even thousands of inputs at once. It's like standing in the center of a massive crowd, each person whispering a different word and somehow making sense of the entire conversation. This integration is where decision-making begins. The dendrites collect information from the neuron's surrounding network and deliver it to the cell body. If the combined input reaches a certain threshold, a critical balance of encouragement and restraint, then the neuron will fire its own signal. But if the balance tilts the other way, if inhibition dominates, the neuron stays quiet. So, the act of listening is not just about receiving. It is about choosing, about discerning what matters and what does not. In this way, dendrites serve as the emotional and intellectual filters of the mind. They are where meaning begins to take shape. They allow you to focus on one voice in a crowd, to notice a single star in the sky, to tune out the noise of the world and hear your own inner thoughts. They are why you don't react to everything all the time, and why you sometimes react to a single word, a glance, a memory, with great intensity. And they are never still. Dendrites are dynamic. They change shape. Their spines grow, retract, multiply, or vanish, depending on your experience. When you learn something new, new dendritic spines form. When you repeat something over and over, those spines strengthen and grow more efficient. When you stop using certain knowledge or skills, the spines fade. Not instantly, but gradually, as the brain makes room for what matters most. This is the physical basis of learning, the very architecture of your attention. Some dendrites grow wide, branching expansively like a tree that catches every drop of rain. Others stay close, tight-knit, specialized for fast, focused input. Some neurons have just a few large dendrites. Others, like pyramidal neurons, have elaborate trees of branches that stretch across layers of the brain. The complexity of a neuron's dendrites often mirrors the complexity of its task. A simple reflex may require only a simple listener, but a nuanced thought, a piece of language, or a philosophical question, that requires a listener with depth, with reach, with sensitivity. And in sleep, dendrites remain awake. During rest, the brain replays experiences from the day, and the dendrites receive this echo. They help consolidate memories, solidify learning, and refine the pathways that will guide your thoughts tomorrow. As dreams unfold, faint sparks revisit the spines that were active earlier, strengthening those that matter, letting go of those that don't. It's as if the dendrites are pruning and sculpting your inner garden while you sleep. Even as you lie here now, Perhaps with eyes closed, your dendrites are working. They are gathering the signals from the outer world, the feel of your sheets, the sound of this voice, the subtle rhythm of your breath. They are also receiving messages from within, the flickers of memories, emotions rising and falling, fragments of old thoughts returning, each one a whisper, each one a possibility. And what's truly humbling is that this listening does not happen in isolation. Each neuron's dendrites are part of a larger community, a vast forest where the trees are aware of one another, not by sight or sound, but by signal. Your entire brain is a listening landscape, each neuron attuned to the needs, rhythms, and stories of those around it. This is the quiet intelligence of the mind, not loud proclamations or rigid commands, but openness, sensitivity, the willingness to be shaped by others, to take in the world, process it deeply, and respond with clarity. So, when you remember something, when you understand something, when you feel a sudden insight light up your mind, remember the dendrites, the listeners of the brain, the quiet architects of awareness. They do not speak, they do not move, but they listen with such depth that meaning itself becomes possible. And tonight, as your consciousness begins to soften and slow, your dendrites remain quietly alive, catching signals in the dark, preparing you for dreams you haven't yet dreamed, and holding space for the thoughts that will shape tomorrow. If dendrites are the quiet listeners of the brain, then the axon is its voice, long, direct, and filled with purpose. It is the messenger's highway, the delivery route of thought, the path that takes the internal and makes it external. Every word you've ever spoken, every muscle you've ever moved, every feeling that surged through your chest, they all began with a signal traveling down an axon. Unlike the branching dendrites that reach outward to receive, the axon is singular, focused. Each neuron has only one axon, but that one structure can stretch an astonishing distance, sometimes over a meter in the human body, from the base of the spine all the way to the tips of your toes. It is a thin, delicate strand, thinner than a human hair, and yet it carries the weight of communication across your entire nervous system. The axon's job is deceptively simple: to transmit. Once a neuron decides to fire, once the dendrites have gathered enough input to reach the threshold, the action potential begins. This is an electrical impulse, a quick and sudden change in voltage that travels down the axon like a lightning bolt through a fiber optic cable. But unlike a lightning bolt, this spark is not destructive. It is a signal, precise and meaningful. The action potential is not a steady stream. It moves in segments, an elegant wave of depolarization and repolarization. As it travels, the charge inside the axon rapidly shifts from negative to positive and back again, opening and closing ion channels in sequence. It's as if each part of the axon is lighting up just in time for the signal to pass through, and then going dark again. This system is made vastly more efficient by the presence of myelin, a fatty insulating sheath that wraps around the axon in segments, like beads on a string. Between each bead is a tiny gap called the node of Ranvier, where the signal momentarily jumps. This jumping, known as saltatory conduction, allows the message to travel up to 100 times faster than it would without myelin. In some ways, the axon is like the neuron's voice box, but far more sophisticated. It doesn't just send a single message. It sends thousands, even millions, each day. It can split at the end into many terminals, allowing one neuron to speak to many others at once. This branching is what allows a single thought to echo across the brain, influencing multiple systems, coordinating movement, emotion, memory, and more, all at once. Consider what happens when you decide to reach for a cup of tea. That single intention triggers a cascade of activity: visual processing to locate the cup, spatial awareness to judge the distance, muscle control to move your hand, and memory to remind you not to grip too tightly. All of this depends on axons transmitting signals to and from the brain, through the spinal cord, out to the muscles, and back again. The moment the cup touches your fingers, sensory axons rush a message back to your brain to confirm the contact. It's a loop of communication so fast and seamless that you don't notice it happening, but it is, always. And yet, the axon is not just a biological wire, it is dynamic, alive. It can grow, retract, regenerate to a limited extent, and even reroute its connections under the right circumstances. After an injury, axons in the peripheral nervous system can sometimes regrow, finding their way back to muscles or skin with surprising accuracy. In the central nervous system, the brain and spinal cord, this process is far more limited, but research shows it's not impossible. The brain holds hidden potential for repair, and the axon plays a key role in that story. The health of axons is essential to every function of the nervous system. When myelin breaks down, as in diseases like multiple sclerosis, the signals slow, weaken, or fail entirely. Movements become difficult, thoughts cloud, fatigue sets in, the clarity of the voice fades. But even in a healthy brain, axons are always at work behind the scenes. Their messages are not always dramatic. Many of them are routine, keeping your heart beating, maintaining posture, adjusting hormone levels, regulating temperature. They don't need applause. They don't ask to be noticed. They simply carry the conversation forward, faithfully, tirelessly, and they do it all in silence. You'll never hear your axons working, but you feel the result of their labor in everything you do. They are the silent runners of the nervous system, swift, precise, efficient, and they are coordinated too. One axon doesn't act alone. It is part of a vast relay, handing off messages to other neurons, to glial cells, to muscles, to organs. The axon's role is temporary. It carries the baton from point A to point B, but without it, nothing would move, nothing would change. And the message it carries is not just data. It is timing, rhythm, urgency. An axon doesn't just say now, it says now, here, this, go. The pattern of its firing, how quickly, how often, in what bursts, encodes meaning. Like Morse code in electricity, the variation in pulse patterns can mean the difference between a gentle touch and a sharp pain, between a calming breath and a racing heartbeat. Even when you're asleep, axons are active. In the deep stages of sleep, long, slow waves of activity sweep through the brain, and axons help coordinate this timing. During dreams, they carry strange and vivid messages between memory centers, visual areas, and emotion processing zones. They are part of the dreaming self, the part of you that swims through story and sensation while your body lies still. Right now, in this very moment, axons are firing across your brain and body. They are sending signals to maintain your heartbeat, to regulate your body temperature, to interpret these very words. They are helping you form images in your mind, to feel calm, to stay alert. You are experiencing the quiet result of billions of microscopic lightning bolts running silently through you. And as you settle deeper into rest, the axons will continue their journey, carrying signals through the darkness, always moving, always guiding, always connecting the moments of your life one after another. They are the threads that tie your thoughts together, the lines that run through your internal dialogue, the silent voice of the neuron, always speaking, always in motion. At the end of the neuron's long journey lies a secret, a moment of transformation that takes place in the smallest of spaces, in the narrow clefts where neurons meet but never touch. It is here, in these tiny gaps called synapses, that the electrical signals traveling down an axon must become something new, a chemical message. And it is here that the neurotransmitters begin their dance, a delicate, fleeting ballet that carries the essence of thought, emotion, sensation, and memory from one neuron to the next. Neurotransmitters are the brain's chemical messengers. They are not random or chaotic. They are specific, purposeful, and exquisitely timed. Each one has a unique structure, a unique message, and a unique place in the story of your inner world. When a neuron fires, it doesn't simply push a button or flip a switch. It releases neurotransmitters, molecules that cross the synapse and bind to receptors on the receiving neuron. This process happens trillions of times a day all across your brain, in loops and layers so intricate that even the most advanced science is still unraveling their mysteries. There are dozens of known neurotransmitters, and likely more yet to be discovered. Each one plays a distinct role, shaping how you feel, what you notice, how you move, and how you remember. Some of these messengers are excitatory, urging the next neuron to fire. Others are inhibitory, encouraging stillness, restraint, calm. The balance between them creates the rhythm of your thoughts, the rise and fall of your emotions, the stability of your attention. Consider serotonin. Often called the feel-good neurotransmitter, it is deeply involved in mood, emotion, and well-being. But serotonin's role is far more nuanced than simply happiness. It regulates sleep, digestion, memory, even social behavior. It flows through circuits that influence anxiety, self-control, and the body's natural rhythm. Too little serotonin and the world feels heavy, uncertain, dim. But in balance, it brings a quiet steadiness, a sense of inner peace. Then there is dopamine, the messenger of motivation and reward. When you anticipate something pleasurable, a bite of your favorite food, a kind word from someone you love, a goal achieved, dopamine surges. It sharpens your focus. It energizes your body. It creates a sense of anticipation and desire. But dopamine doesn't just respond to rewards. It helps you learn from them. Every time something unexpectedly good happens, dopamine helps your brain remember what led to it so you can seek it again. It fuels curiosity, exploration, ambition. Yet too much dopamine, especially in the wrong circuits, can tip the mind into obsession, addiction, or manic energy. Another key player is GABA, or gamma-aminobutyric acid, the brain's main inhibitory neurotransmitter. If dopamine is the voice that says go, GABA is the gentle whisper that says slow down. It quiets excess activity, soothes overexcited neurons, and creates the spaciousness needed for calm and stillness. Without GABA, the brain would be overwhelmed by noise, a constant buzz of uncontrolled firing. GABA brings serenity to the storm, helping you sleep, meditate, breathe deeply, and find rest. Then there's glutamate, the most abundant excitatory neurotransmitter in the brain. It is involved in nearly every aspect of cognition, learning, memory, attention, and more. Glutamate sharpens signals, strengthens synaptic connections, and builds the pathways that form your understanding of the world. But like fire, it must be carefully contained. Too much glutamate can lead to overexcitation and even damage. Its power lies in its precision, just the right amount, at just the right time. There are others too. Norepinephrine, which heightens alertness and primes the body for action in times of stress. Acetylcholine, essential for attention and muscle control. Endorphins, which ease pain and bring feelings of pleasure. Oxytocin, often called the love hormone, which enhances bonding and trust. Each neurotransmitter is part of a vast, interwoven system of influence and response, constantly adjusting to your environment, your choices, and your inner world. But neurotransmitters do more than send messages. They shape the brain itself. Every time you learn, remember, feel, or act, neurotransmitters help determine which neural pathways are reinforced, which ones fade, and how efficiently signals are sent. They help decide which experiences are stored, which are ignored, which are marked as important, and which are left behind. And their effects are not always immediate. Sometimes, a neurotransmitter primes a neuron to be more or less sensitive in the future, setting the stage for how you'll respond later. This is how mood patterns form, how trauma leaves its mark, how repeated thoughts become beliefs. Neurotransmitters don't just pass through, they linger, adapt, transform. Even the tiniest release can matter. A few molecules of dopamine in the right place can change your mood for hours. A rush of serotonin after a long walk in the sun can soften your thoughts. A balance of GABA during meditation can lull you into deep peace. These chemicals are not foreign. They are not imposed from outside. They are you, your biology, your experience, your story told through molecules. And they work together. Rarely does one act alone. In every moment, your brain blends multiple neurotransmitters in precise combinations, like a symphony of invisible instruments, tuning your perception of reality. Your emotions are not random. They are chemical chords, shaped by the ever-changing harmony of these molecular messengers. This dance happens in silence, in darkness, within the tiny gaps between cells, and yet it creates the entire symphony of your inner life. Even now, as you lie still and quiet, neurotransmitters are moving through your brain. They are calming your breath, adjusting your heart rate, easing your body toward rest. They are helping you process these words, attaching meaning, perhaps even emotion, to the thoughts that rise and fall in your awareness. As sleep approaches, the balance shifts again. Melatonin begins to rise, dimming the lights inside your brain. GABA becomes more prominent, soothing your circuits. Serotonin helps regulate your circadian rhythm. Your thoughts begin to soften. Your body relaxes. The outer world fades. And through it all, neurotransmitters carry the final messages of the day, a whisper of gratitude, a last flicker of reflection, the quiet invitation of sleep. These tiny molecules are your companions in every moment, from your first memory to your last dream. They are the unseen language of the self, speaking not in words, but in waves, in chemistry, in connection. And tonight, they continue their work, gently, quietly, endlessly, writing your story from within. Imagine a soft glow pulsing gently in the background of your mind. Not loud, not intense, but steady. This glow is not visible. It doesn't shine with light, but with feeling. It brings a sense of balance, of ease, of quiet contentment. This is serotonin, the soft song of the brain. Serotonin is one of the most well-known neurotransmitters, and yet its true nature is often misunderstood. Often called the happiness chemical, serotonin's role is far more intricate than a simple feeling of joy. It is not a single note of bliss, but a melody, subtle, complex, and deeply woven into nearly every system of the body and brain. The story of serotonin begins in the brainstem, in a small cluster of neurons known as the Rafe nuclei. From this modest origin, serotonin-producing neurons extend long axons throughout the brain, into the limbic system, the cortex, the hippocampus, the thalamus. These projections are like vines, spreading a gentle influence in every direction. The reach of serotonin is vast, and its impact profound. But what does serotonin do? Its role is not to create happiness outright. Instead, serotonin helps stabilize your mood. It smooths the rough edges of emotion, gives resilience to the mind, and helps keep your thoughts from spiraling into chaos. When serotonin levels are balanced, you may not feel euphoria, but you feel grounded, calm, and capable of navigating life's ups and downs with clarity. It acts like an emotional anchor, keeping your mental boat steady even as the waters of experience shift beneath you. Serotonin influences many of the most essential aspects of being human. It helps regulate sleep cycles, allowing you to drift into slumber and rise again with the sun. It affects your appetite, digestion, pain perception, memory, and even your sense of social connection. This single molecule touches every corner of your life, from your ability to focus, to your desire for companionship, to your capacity for hope. One of serotonin's most intriguing roles lies in its connection to the sense of self. Research suggests that serotonin plays a key part in regulating the default mode network, the brain system involved in self-reflection, introspection, and internal dialogue. When serotonin levels are healthy, the mind is able to look inward without getting lost. You can reflect without ruminating, dream without detaching, imagine without forgetting who you are. Low serotonin levels, on the other hand, are associated with depression, anxiety, irritability, and even obsessive thought patterns. When serotonin is scarce, the soft song becomes distorted. Thoughts loop, emotions crash. The inner world becomes harder to navigate. And yet, even in such moments, serotonin never stops trying. It is a persistent, gentle force, one that works quietly to restore balance. Serotonin's work is not done alone. It is part of a vast symphony of neurotransmitters. It harmonizes with dopamine to manage reward and motivation. It balances with GABA to promote calm. It interacts with cortisol, the stress hormone, to keep your responses from tipping too far in one direction. It is not the loudest instrument in the brain's orchestra, but it is one of the most constant, the cello beneath the violin, the rhythm beneath the melody. What's more, serotonin doesn't just live in the brain. In fact, over 90% of the body's serotonin is found in the gut. The enteric nervous system, often called the second brain, produces and uses serotonin to help regulate digestion, absorption, and gut motility. The connection between gut and brain is deep, and serotonin is one of the threads that binds them together. This is why your mood can change after eating, or why stress can cause digestive discomfort. The soft song of serotonin plays in both places at once. Its influence is even tied to light. Exposure to sunlight triggers serotonin production. That's why a walk outdoors can lift your mood, and why long, dark winters can sometimes bring feelings of heaviness or melancholy. Serotonin responds to the rhythm of the day, aligning your internal world with the movement of the world around you. Even moments of quiet pleasure, the smell of something nostalgic, the feeling of warm water, the sound of your favorite voice, can prompt the brain to release a little more serotonin. Not in a rush, not in a burst, but in a soft wave. This is its nature: subtle, gentle, enduring. Serotonin also plays a role in your capacity for kindness, patience, and connection. Higher serotonin levels are associated with greater empathy and social bonding. This may be why acts of compassion, even small ones, can feel good. They resonate through your system, affirming your place in the web of life, not through grand emotion, but through a deep, quiet sense of belonging. As you prepare for sleep, serotonin continues its work. It helps convert into melatonin, the hormone that regulates your circadian rhythm. This transition is not abrupt. It is smooth, graceful, like a lullaby turning into a dream. The same neurotransmitter that steadied you through the day now gently guides you into the night. Right now, as you rest, serotonin is working quietly behind the scenes. It is calming your thoughts, softening your muscles, regulating your heartbeat. It is preparing you for healing, for memory consolidation, for dreams. Its song cannot be heard with ears. It can only be felt as a sense of peace, of trust, of soft surrender to the present moment. You do not need to control serotonin. You do not need to chase it. You only need to care for the body and mind that create it, with rest, with light, with nourishing food, with love. And in return, serotonin will continue to hum beneath your awareness. It is the soft song of balance, of peace, of quiet strength. And tonight, it sings you to sleep. There's a feeling you've had many times, though you might not have noticed it at first. It arrives not as a grand revelation, but as a flicker, a burst of satisfaction after solving a puzzle, a wave of pleasure when someone praises your effort, a surge of joy when something you've hoped for finally happens. Behind each of these moments is a messenger, fast, sharp, and full of meaning. This is dopamine, and it is the brain's way of saying, yes, that was good. Do it again. Dopamine is often called the reward chemical, but its true role is much deeper and more dynamic. It's not simply a response to pleasure. It is the force that drives us toward pleasure. It is the expectation of joy, the tension before release, the spark of motivation that pushes you toward the future. If serotonin is the steady rhythm that keeps you grounded, dopamine is the rising crescendo, the signal that something important is just ahead. Unlike neurotransmitters that calm or stabilize, dopamine is a stimulant. It energizes circuits. It awakens attention. It fuels effort. It is what makes you curious, goal-directed, ambitious. Without dopamine, there would be no desire to pursue anything, no urge to learn, to try, to change. It is the fuel for action. Dopamine originates in a few small but mighty regions of the brain, particularly the ventral tegmental area, VTA, and the substantia nigra. From there, it travels along powerful neural highways to the nucleus accumbens, the prefrontal cortex, the amygdala, and beyond. These pathways form the brain's reward system, the circuitry responsible for evaluating outcomes, forming habits, and shaping motivation. But dopamine does not just appear when something good happens. In fact, it is most active before the reward is received. The moment you sense a possible reward, the smell of food when you're hungry, the sound of a message notification, the first glimpse of someone you love, dopamine surges. This surge doesn't feel like fulfillment. It feels like anticipation, excitement, the readiness to act. Dopamine is not about having. It is about wanting. And it is precisely this quality that makes dopamine so powerful and so dangerous, because dopamine is sensitive to prediction. If a reward is expected and it arrives, dopamine rises moderately. But if a reward is better than expected, dopamine spikes. The brain takes notice. It learns. It rewires. It wants more. On the other hand, if a reward is expected but doesn't arrive, dopamine levels crash. You feel disappointed, frustrated, even angry. This is the emotional swing of expectation, the reason a surprise gift can make your day and a broken promise can ruin it. Your brain is constantly adjusting its predictions and updating its wiring based on what dopamine teaches it. Over time, this becomes the blueprint of your desires. But not all dopamine-driven behavior is joyful or healthy, because dopamine is more about pursuit than fulfillment. It can easily become unbalanced. This is how addictions form, whether to substances, screens, or even validation. When the brain is repeatedly flooded with dopamine through unnatural means, it adapts by reducing sensitivity. The same amount of stimulation no longer satisfies. More is needed, then more, and more. The pursuit continues, but the joy fades. And yet, at its core, dopamine is not the enemy. It is a teacher, a compass, a guide. It teaches you what to value based on what has worked in the past. It rewards effort, not just success. A student learning a new language, a musician perfecting a piece, a child stacking blocks. All are powered by dopamine. Not because the task is easy, but because it offers progress. Forward movement. A sense of growing towards something. Dopamine also helps you remember what matters. It strengthens the synapses involved in pleasurable experiences, reinforcing them so they're easier to access later. That's why you remember the smell of your favorite meal, the place where you fell in love, the feeling of finishing a hard task. Dopamine not only motivates, it cements meaning. It even shapes identity, what you crave, what you strive for, what you chase. These are not just habits. They become part of who you are. The artist seeking beauty, the scientist seeking truth, the traveler seeking new horizons. Each identity is built upon countless dopamine-fueled choices, woven into the architecture of your brain. And dopamine works best in balance. Too little, and life feels flat, aimless. Everything becomes effort. This is often seen in conditions like Parkinson's disease or certain types of depression, where dopamine-producing neurons are diminished. But too much dopamine, especially in certain areas of the brain, can lead to impulsivity, risk-taking, even delusion. The mind must walk a careful line between motivation and obsession, desire and restraint. Sleep plays a key role in maintaining this balance. At night, the brain resets its dopamine receptors. It reorganizes the day's experiences, processes rewards, and prepares for new learning. This is why a good night's rest can restore motivation, and why chronic sleep deprivation leaves you feeling foggy, unmotivated, or emotionally dull. Even as you lie here now, in this moment of stillness, dopamine continues its quiet work. It may be recalling something you accomplished today. It may be preparing a pathway for tomorrow's goal. It may be reinforcing the reward of relaxation itself, teaching you that stillness too has value. And when you wake, refreshed, dopamine will return again, not just to push you toward productivity, but to give shape to your desire, to help you move toward what matters, to offer a sense of direction, of effort with purpose. It is the spark of the chase, the joy of effort, the warmth of growth. And perhaps most beautifully, dopamine does not require external rewards. You can train it, cultivate it. When you find meaning in small steps, joy in simple things, purpose in the journey itself, dopamine becomes your ally, not your master. Tonight, as the body rests and the mind drifts into the landscape of dreams, dopamine is still listening, still shaping, still guiding you forward in the most silent of ways. Not with force, but with fire. Not with noise, but with a signal. Go. Try. Reach. Grow. In the symphony of the brain, where neurons fire and messages fly, there is a voice that speaks softly, a whisper that brings calm, order, and balance. This is GABA, the brain's primary inhibitory neurotransmitter. While much attention is given to the signals that excite and stimulate, GABA is equally vital because it is the quieting force, the gentle brake that prevents the nervous system from spiraling into chaos. Imagine your brain as a bustling city, alive with the hum of traffic, the chatter of crowds, the clatter of daily life. Without traffic lights, crosswalks, or rules, that city would descend into disorder. Similarly, your brain depends on GABA to regulate the flow of electrical impulses, to slow down overactive neurons, and to create spaces of rest within the ongoing storm of activity. When a neuron releases GABA, it binds to specific receptors on neighboring neurons, opening channels that allow negatively charged ions to enter. This influx makes it harder for the receiving neuron to fire an action potential. In essence, GABA says, pause, wait, slow down. This inhibitory action is crucial for maintaining the delicate balance between excitation and inhibition that underpins healthy brain function. Without GABA, the brain would be overwhelmed by noise, a constant barrage of signals with no relief. This imbalance is at the root of many neurological and psychiatric conditions: seizures, anxiety disorders, insomnia, and even some forms of depression can be traced to disruptions in GABA signaling. It is the balance that keeps the mind stable, focused, and calm. But GABA's role goes beyond mere inhibition. It shapes the quality of your experience. When you feel relaxed after a deep breath, when your mind settles into meditation, When you drift peacefully into sleep, GABA is at work. It softens the electrical chatter, creates moments of silence, and helps you feel grounded in your body and present in your mind. The calming influence of GABA is also linked to your body's natural responses to stress. When you encounter a threat, your nervous system ramps up, releasing excitatory neurotransmitters and activating fight or flight responses. GABA works to counterbalance this surge, to bring you back to a state of equilibrium once the danger has passed. It helps modulate your heart rate, your breathing, and your muscle tension, guiding you from heightened alertness back to rest. This inhibitory neurotransmitter also plays a vital role in shaping learning and memory. By regulating the timing and synchronization of neural firing, GABA ensures that signals are precise and meaningful rather than noisy and confusing. It filters out irrelevant information, allowing your brain to focus on what matters. This selective inhibition is essential for attention, problem-solving, and the ability to shift flexibly between tasks. Interestingly, GABA's influence is not static. Its receptors are dynamic, adjusting their sensitivity based on experience, mood, and even time of day. Certain medications and substances, like benzodiazepines or alcohol, enhance GABA's effects, which is why they induce relaxation and sedation. But the natural balance of GABA in the brain is far more nuanced, finely tuned to maintain optimal function without dulling awareness. The production and regulation of GABA also depend on your overall health. Nutrition, exercise, sleep, and stress management all influence how well this neurotransmitter performs. A healthy lifestyle supports robust GABA activity, fostering mental clarity, emotional stability, and restful sleep. Even during sleep, GABA's work continues. It helps initiate and maintain deep sleep stages, promoting the restorative processes that rejuvenate the brain and body. Without GABA, the mind would remain restless, unable to enter the peaceful cycles necessary for healing and memory consolidation. Right now, as you rest quietly, GABA is gently guiding your neurons into a slower rhythm. It is softening the edges of thought, easing the flow of signals, and preparing your brain for the silence of deep sleep. It is the calm in the center of the storm, the breath between words, the space where peace can grow. In the grand language of your brain, GABA's voice is soft but profound. It tells your neurons to listen, to wait, to be still. It creates the quiet moments that make life meaningful, moments of reflection, of calm, of rest. In the complex language of the brain, where whispers and sparks intertwine, there exists a messenger of power and possibility: glutamate. It is the most abundant excitatory neurotransmitter, the spark that ignites thought, memory, learning, and the very essence of cognition. Without glutamate, the brain would be a dim, silent place. With it, the mind lights up, connects, and grows. Glutamate's role in the brain is profound. It acts as the primary catalyst for excitation, encouraging neurons to fire and communicate. When a neuron releases glutamate into the synapse, it binds to specialized receptors on the receiving neuron, such as NMDA and AMPA receptors, triggering an influx of positively charged ions. This influx depolarizes the neuron, making it more likely to generate an action potential. In other words, glutamate is the green light that says, "Go ahead, pass the message." This excitatory action is essential for brain function. Glutamate drives the processes that allow you to perceive the world, solve problems, focus your attention, and remember your experiences. It is the neurotransmitter of learning, forming the foundation of neuroplasticity, the brain's remarkable ability to adapt and change in response to experience. At the heart of learning lies a process called long-term potentiation, LTP. This is where repeated stimulation of synapses by glutamate strengthens the connection between neurons, making future communication more efficient. Imagine a path through a forest that becomes clearer and easier to follow each time you walk it. This is how memories are formed and skills are learned. Glutamate is the guide, lighting the way, encouraging the neurons to fire together and forge lasting connections. Yet, with such power comes responsibility. Glutamate's excitatory nature means that it must be carefully regulated. Too little glutamate, and the brain's communication falters, leading to cognitive difficulties, memory loss, and a dulling of mental sharpness. Too much glutamate, however, can be harmful, causing excitotoxicity, a toxic overload that damages or kills neurons. Excitotoxicity is involved in various neurological disorders, including stroke, traumatic brain injury, epilepsy, and neurodegenerative diseases like Alzheimer's and Parkinson's. When neurons are overstimulated by excessive glutamate, calcium floods the cell, triggering a cascade of destructive processes. The delicate balance of glutamate activity is vital to maintaining brain health. This balance is maintained by a complex system of glutamate reuptake and recycling. Specialized cells called astrocytes surround synapses and absorb excess glutamate, converting it into glutamine, which can then be safely transported back to neurons for reuse. This cycle ensures that glutamate signals remain precise and controlled, preventing the chaos of overexcitation. Glutamate's influence extends beyond cognition. It plays a role in mood regulation, pain perception, and motor control. Its receptors are found throughout the brain, involved in circuits that govern everything from the coordination of movement to the processing of emotions. Interestingly, glutamate also interacts closely with other neurotransmitters. It works alongside GABA, the inhibitory counterpart, to maintain the brain's balance between excitation and inhibition. Together, they orchestrate the rhythm of neural activity, ensuring that the brain neither lulls into silence nor erupts into uncontrolled noise. In the realm of consciousness, glutamate's role is vital. It supports the networks involved in attention, awareness, and sensory processing. It helps the brain focus on what matters, filtering information from the environment and enabling you to respond effectively. Without glutamate, perception would fade and the richness of experience would diminish. During sleep, glutamate continues its work in quieter rhythms. It supports the replay of neural patterns, the reactivation of memories and experiences that help consolidate learning and emotional processing. This replay is thought to underlie dreaming, where fragments of waking life are woven into the vivid tapestries of the mind. Right now, as you rest, glutamate is participating in countless conversations within your brain. It helps encode the impressions of this moment, reinforcing the neural pathways that link understanding, emotion, and awareness. It is the fuel behind your ability to absorb these words, to reflect on their meaning, and to carry the ideas with you as you drift towards sleep. In the vast orchestra of your mind, glutamate is the bright, clear note, the spark that ignites the symphony. It is both delicate and powerful, simple and complex, quiet yet indispensable. It drives the creation of memory, the shaping of thought, the expansion of consciousness. And as the night deepens, this messenger of excitation works silently, weaving the patterns that will become your dreams, your insights, yourself. Memory is one of the most remarkable gifts your brain offers, a vast library of experience, sensation, emotion, and meaning, all woven together in a delicate tapestry of neurons and synapses. But memory is not simply a static storage room where facts are filed away. It is a living, breathing process. A whispering dance of electrical and chemical signals, continuously reshaped by time and use. And at the heart of this dance lies the quiet art of how memories are whispered into being. When an experience occurs, a sight, a sound, a touch, a feeling, it triggers a cascade of neuronal activity across multiple regions of the brain. These regions work together, forming networks that encode different aspects of the event: the sensory details, the emotional tone, the context, the meaning. The hippocampus, often called the brain's librarian, plays a critical role in organizing this information, linking fragments into a coherent whole. But encoding a memory is only the first step. The brain must also consolidate it, transforming a fragile trace into a durable imprint. This is where neurons speak in patterns, whispering the details of the experience repeatedly, strengthening the connections between them. These whispers travel back and forth across synapses, reinforcing circuits, shaping the architecture of the brain. The phrase, "neurons that fire together, wire together," captures this beautifully. When groups of neurons activate simultaneously, their synaptic connections become stronger, more efficient. It's a process called synaptic plasticity, and it forms the physical basis of learning and memory. Each time you recall a memory, each time you practice a skill, these connections are rehearsed and refined. The whisper grows louder, clearer, more reliable. Memory is not stored in one place, but distributed across the brain. Sensory cortices hold the details of what you saw or heard. The amygdala records emotional significance. The prefrontal cortex integrates memories with goals and context. Together, these regions create a dynamic network, a living map of your past. But memories are not perfect recordings. They are reconstructive, malleable, shaped by each telling. Every time you remember something, you recreate it, influenced by your current thoughts, feelings, and environment. Memories can change, fade, or become distorted. This is the nature of the whisper. It is intimate and flexible, not fixed and rigid. Sleep plays a vital role in memory consolidation. During deep sleep, the brain replays patterns of activity from waking life, silently rehearsing and reinforcing important memories while pruning away unnecessary ones. This nightly whispering helps transfer memories from the hippocampus to the cortex, where they become more stable and integrated into your broader knowledge. Even during wakefulness, the brain continues to whisper memories in subtle ways. When you daydream, when you reflect, when you make decisions, your brain draws on these silent conversations to guide you. Past experiences inform your choices, shape your beliefs, and color your emotions, all carried on the quiet waves of neuronal whispers. The way memories are whispered into being also explains why practice matters. Repetition strengthens the synaptic bonds, making recall easier, faster, and more vivid. Learning a new language, Mastering an instrument or developing a skill requires countless whispers, repeated activations of the relevant neural networks, deepening their connections. Yet memory is not just about preservation, it is about creation. Your brain can combine fragments of old experiences to imagine new possibilities, to simulate future events, to dream. This constructive nature is essential for creativity, problem-solving, and adaptation. Emotions play a crucial role in memory as well. Events that carry strong feelings, joy, fear, surprise, are more likely to be remembered. The amygdala modulates the strength of synaptic connections during these moments, turning up the volume on certain whispers to ensure they are not forgotten. This is why emotional memories often feel vivid, immediate, and enduring. But the whisper of memory can also be fragile. Stress, trauma, aging, and disease can disrupt the delicate balance of neuronal communication. Memory loss, confusion, and cognitive decline arise when the synaptic whispers grow faint, misaligned, or silent. Scientists are still unraveling the mysteries of how to protect and restore these connections, seeking ways to keep the library of the mind alive and accessible. Right now, as you rest, your brain continues this work silently. It rehearses the moments of the day, strengthens important connections, weaves new patterns, and clears away what is no longer needed. This nightly whispering ensures that your memories are not lost, but transformed, ready to guide you tomorrow. In the vast, quiet symphony within, memories are not shouted, they are whispered, delicately, patiently, persistently, every moment of your conscious experience. The sight of a sunset, the sound of a friend's voice, the warmth of a gentle breeze, is born from an astonishing journey deep within your brain. This journey is a passage through the complex pathways of countless neurons, each firing in precise sequences, weaving together the sensations, thoughts, and feelings that create your reality. At the heart of this journey lies the silent, intricate voyage of a neuron traveling across the brain. Imagine a single neuron waking from rest. Its dendrites reach out, receiving whispers of signals from neighbors, fragments of light, touch, sound, or memory. When the input is sufficient, this neuron fires an electrical pulse, an action potential that surges down its axon, traveling like a bolt of lightning through its long, slender extension. This signal must reach its destination, another neuron somewhere else in the brain, to pass along its message and keep the conversation alive. But the path is far from simple. The axon twists and turns, branching at times, crossing complex networks, sometimes covering remarkable distances. A neuron in the visual cortex, for example, may send its message to the frontal lobe, where conscious decision-making happens. Others may connect to the limbic system, stirring emotion, or to the motor cortex, initiating movement. Each connection is a crucial link in the chain, a step on the neuron's journey towards shaping your experience. Along this path, the signal encounters synapses, microscopic gaps where it must be transformed from electricity into chemistry and back again. At each synapse, neurotransmitters are released, crossing the cleft and binding to receptors on the next neuron, prompting it to fire or to hold silent. This relay continues, neuron to neuron, forming networks that encode everything from simple reflexes to complex, abstract thought. This journey is not random. It follows patterns refined over millennia of evolution and shaped by your unique experiences. Some pathways are ancient, hardwired to regulate vital functions like breathing, and heartbeat. Others are flexible, shaped by learning and memory, constantly rewired as you grow and adapt. The voyage of a neuron signal can also vary in speed and intensity. Myelinated axons, wrapped in insulating layers called myelin, conduct impulses faster, ensuring rapid communication for urgent signals. Unmyelinated axons transmit more slowly, suited for less immediate messages. This variation allows the brain to prioritize its countless communications efficiently. Moreover, neurons often branch at their axon terminals, allowing a single message to be broadcast to multiple neurons simultaneously. This branching is essential for coordinating complex behaviors, enabling different brain regions to work in harmony. It is how a thought can ripple outward, influencing emotion, perception, and action all at once. This vast network of connections is sometimes called the connect-to-me, the map of all neuronal pathways in your brain. It is one of the most intricate systems known, with an estimated 150 trillion synapses forming the highways and byways for neuronal signals. Every signal that travels along these routes is part of your inner narrative, your sense of self, your awareness of the world. But the journey of a neuron signal is not just about transmitting information, it is also about transformation. Along the way, the signal can be amplified, inhibited, modulated by chemicals, or shaped by the timing of other signals. This dynamic interplay allows your brain to interpret sensory input in context, to filter noise, to prioritize important information, and to create a coherent experience from the chaos of the world. In addition, the neuron's journey is influenced by glial cells, the unsung heroes of the nervous system. These cells support neurons, maintain their environment, and even modulate synaptic activity. They clear away waste, supply nutrients, and help repair damage. Together, neurons and glia form a complex ecosystem, a delicate balance that sustains thought and life. The voyage of neuronal signals also underlies your ability to learn and change. With every new experience, new connections are formed. Existing ones are strengthened or weakened. This plasticity means that the path your neuron signals take today may differ from yesterday, adapting to your growing understanding, your shifting emotions, and your evolving self. Even in rest, the brain's activity continues. During sleep, signals replay in loops, rehearsing the day's experiences, consolidating memories, and preparing the brain for future challenges. The neuron's journey becomes a nightly ritual of refinement, pruning, and strengthening. Right now, as you breathe quietly, your neurons are on their journeys, crossing synapses, sparking in patterns, carrying the sensations of this moment into the deeper realms of your mind. They are telling the story of who you are, moment by moment, signal by signal. This journey is invisible, silent, but it is the foundation of consciousness, the road upon which your inner life travels. Learning is a dance of change, a continual process where your brain adapts, rewires, and grows in response to experience. At the heart of this transformation lies a remarkable principle: plasticity. Neuroplasticity is the brain's ability to reshape itself, to form new connections, to strengthen existing pathways, and even to prune away those no longer needed. It is the physical basis for every skill you acquire, every habit you build, every insight you gain. When you first encounter something new, a language, a melody, a face, your neurons light up in novel patterns. These initial activations are fragile, like a tentative step onto unknown ground. But with repetition, these pathways become more stable, more efficient. Synapses strengthen, dendritic spines grow, axons branch. The brain literally rewires itself, creating highways where once there were only footpaths. This is how learning is written in the language of neurons. Neuroplasticity is not confined to childhood, as once believed. While young brains are especially malleable, capable of rapid growth and change, plasticity continues throughout life. Adults can learn new skills, recover from injury, and even alter deeply ingrained habits, all through the dynamic interplay of neuronal activity and synaptic modification. At the cellular level, learning involves long-term potentiation, LTP, a process where repeated stimulation strengthens synapses, making future transmissions easier and faster. It is a form of cellular memory. When two neurons fire together repeatedly, the connection between them becomes more sensitive. This fire together, wire together principle allows the brain to encode patterns, associations, and sequences. But learning is more than just strengthening connections. It also involves pruning, the elimination of weaker or unnecessary synapses. This selective refinement sharpens neural circuits, enhancing efficiency and focus. The brain is both builder and sculptor, constantly balancing growth and reduction to optimize performance. Neuroplasticity is influenced by attention, emotion, and motivation. When you focus deeply on a task, your brain releases neurotransmitters like dopamine and acetylcholine, which enhance synaptic plasticity. Emotional significance acts as a powerful catalyst, marking certain experiences as important and prioritizing their encoding. Motivation fuels repetition, practice, and exploration, reinforcing the pathways that lead to mastery. Learning can take many forms, from explicit instruction to implicit adaptation. It can be conscious or unconscious. Sometimes it is slow and deliberate. Other times it is rapid and intuitive. Regardless of how it happens, the underlying mechanism is the brain's remarkable ability to rewire itself, forging new paths and revising old ones. This plasticity also underlies recovery from injury. When parts of the brain are damaged, nearby neurons can sometimes take over lost functions, reorganizing their connections to compensate. Rehabilitation therapies harness this potential, encouraging new patterns of activity to rebuild abilities. However, plasticity is a double-edged sword. While it enables growth, it can also reinforce negative patterns, habits, fears, addictions, if repeated often enough. The brain's adaptability means it learns what you practice, whether helpful or harmful. This is why intentional practice and mindful awareness are crucial for positive change. Sleep plays a vital role in neuroplasticity. During deep sleep and REM phases, the brain consolidates learning, strengthens important connections, and clears metabolic waste. These restorative processes are essential for solidifying memories and skills. Environmental factors also impact plasticity. Enriched surroundings, social interaction, physical exercise, and mental stimulation all promote synaptic growth and cognitive flexibility. Conversely, stress, isolation, and lack of stimulation can impair plasticity, leading to cognitive decline. At a broader scale, neuroplasticity shapes your identity. Each new experience subtly rewrites your brain's wiring, influencing your thoughts, behaviors, and perceptions. Over time, these changes accumulate, crafting the evolving story of who you are. Even as you rest now, your brain is not idle. It rehearses recent experiences, adjusts synaptic strengths, and prepares for future challenges. This ongoing plasticity means you are never fixed or finished, always becoming, always learning. Sleep is one of the most mysterious and essential states your brain enters, a nightly voyage into silence and renewal. But beneath the stillness of closed eyes lies a bustling world of activity, a hidden symphony where neurons continue their whispers, playing the quiet, intricate language of rest. This is the time when your brain shifts its focus, turning inward to perform vital maintenance, healing, and memory work. It is in this darkness that neurons tell secrets, sharing messages not with the urgency of waking life, but with the gentleness of restoration. When you fall asleep, your brain transitions through stages, each marked by distinct patterns of neuronal activity. The initial stage is light sleep, where the brain begins to slow, neurons firing less frequently and in more synchronized rhythms. As you descend deeper into slow-wave sleep, neurons synchronize their firing in large, slow oscillations, a wave-like rhythm that sweeps across the cortex like a gentle tide. This slow-wave sleep is a time of profound rest, when the brain's activity diminishes and energy consumption drops significantly. Yet even in this apparent quiet, neurons are not silent. They whisper rhythms that help consolidate memories and restore balance. The deep sleep phase is thought to serve many critical functions. It supports the clearance of metabolic waste products that accumulate during waking hours, helping to maintain the health of neurons and the brain's environment. It facilitates the consolidation of declarative memories, the facts and events you consciously recall. During this time, the hippocampus and cortex engage in a dialogue, replaying the patterns of neuronal firing experienced during the day, reinforcing important connections and pruning away less relevant ones. It is as if your brain is softly rehearsing the day's lessons, strengthening the networks that will serve you tomorrow. Following deep sleep comes REM sleep, the stage of vivid dreaming. Here, neuronal activity becomes more irregular and intense, resembling patterns seen during wakefulness. Neurons fire in complex, often unpredictable sequences, weaving together fragments of memory, emotion, and imagination into the rich tapestry of dreams. These dream states are thought to play a role in emotional regulation, creativity, and problem-solving. The brain uses this time to process unresolved feelings and integrate experiences, giving shape and meaning to the unconscious. Throughout sleep, different neuronal populations modulate their activity in a carefully orchestrated balance. Inhibitory neurons increase their influence, calming certain circuits while allowing others to become active. This dynamic gating ensures that sleep is not a uniform shutdown, but a selective process where some areas rest deeply while others engage in vital functions. Moreover, sleep supports synaptic homeostasis, the delicate balancing act of strengthening some synapses while weakening others to prevent saturation. This balance preserves the brain's ability to learn and adapt, ensuring that waking experiences can continue to be encoded without overwhelming the system. The brain's electrical rhythms during sleep are diverse and layered. Slow oscillations, sleep spindles, and sharp wave ripples each play roles in coordinating neuronal communication. These rhythms act as a hidden language, synchronizing activity across regions and promoting the transfer of information. For instance, sleep spindles, brief bursts of oscillatory activity, are associated with memory consolidation and cognitive performance. As you rest, your brain's metabolic demands decrease, but energy-intensive processes like protein synthesis and cellular repair increase. Neurons rebuild membranes, replenish neurotransmitters, and remove damaged components. Sleep is the brain's workshop, where the cellular machinery is maintained and optimized. This nocturnal whispering of neurons is essential for mental health, emotional resilience, and cognitive function. Chronic sleep deprivation disrupts these processes, leading to impaired memory, reduced attention, mood disturbances, and increased risk of neurodegenerative diseases. The restorative power of sleep cannot be overstated. Even as you lie here now, the neurons in your brain are engaged in this secret language. They are slowing their rhythms, coordinating their signals, replaying your day's experiences, and preparing your mind for tomorrow. The outer world fades, but inside, the whispers grow clearer, gentle pulses guiding you into deeper rest. Sleep is not merely the absence of wakefulness. It is a vibrant state of neuronal conversation, a time when the brain tells its secrets, heals its wounds, and renews its strength. In this darkness, the language of your neurons becomes a lullaby, soft, persistent, and full of promise. And as you drift deeper, carried by the silent whispers of your mind, you are cradled in the gentle embrace of the night. Dreams unfold in a realm where the boundaries between reality and imagination dissolve, a space crafted by the subtle interplay of neuronal activity deep within the sleeping brain. Though we often think of sleep as a time of silence and rest, during certain phases, particularly REM sleep, neurons burst into vivid patterns of firing that create the rich, sometimes bewildering experiences we call dreams. These dreams are more than fleeting images. They are profound expressions of the brain's hidden language, a secret dialogue that reveals much about memory, emotion, and consciousness itself. As you drift into REM sleep, the brain's electrical rhythms change dramatically. Neurons fire rapidly and irregularly, mimicking the activity patterns of wakefulness, but with a distinct difference. The brain's sensory inputs from the outside world are largely shut off, and the normal executive control of the prefrontal cortex is subdued. This creates a unique neural environment, one where the mind can roam freely, unhindered by external reality or logical constraints. In this state, the brain weaves together fragments of recent experiences, distant memories, emotions, and even abstract concepts into vivid sensory scenarios. The hippocampus, responsible for memory formation and consolidation, plays a key role here. During dreaming, it reactivates sequences of neuronal firing that occurred during waking life, replaying experiences in compressed, often scrambled fashion. This replay supports memory consolidation, but also provides raw material for the creative recombination seen in dreams. The emotional centers of the brain, such as the amygdala, are highly active during REM sleep, coloring dreams with strong feelings, fear, joy, curiosity, or confusion, often amplifying their intensity beyond waking experience. This emotional vividness explains why dreams can feel so real, so urgent, and sometimes so unsettling. They tap into deep wells of feeling, stirring unconscious fears and desires. At the same time, the reduced activity of the prefrontal cortex, the brain's logical overseer, means that during dreams, bizarre and impossible scenarios are accepted as normal. The usual filters of rational thought are loosened, allowing for fluid, symbolic, and often paradoxical narratives. Neurons in the visual cortex fire in patterns that conjure images, colors, and scenes. Those in the auditory areas create sounds, voices, music. Motor areas activate even though the body remains largely paralyzed, producing the sensation of movement or action. This complex orchestration results in the immersive experiences we associate with dreaming, walking through landscapes, engaging in conversations, flying, or confronting fears. Dreams serve several vital functions. Beyond their role in memory consolidation, they may help the brain process emotions, work through unresolved conflicts, and simulate scenarios for future planning. By replaying and recombining past experiences, dreams allow the brain to explore possibilities without risk, fostering creativity and problem-solving. Some theories suggest dreams act as a form of emotional therapy, providing a safe space to confront difficult feelings and integrate them into the psyche. The language of dreaming neurons is rich and multi-layered. It involves bursts of rapid firing interspersed with slower oscillations, coordinating activity across widespread networks. Sharp wave ripples in the hippocampus synchronize with sleep spindles in the cortex, facilitating communication that underlies the transfer and integration of memories. This interplay reflects a deeply complex dialogue, one that transcends simple signal transmission to encompass meaning, feeling, and imagination. Even as the night progresses, the content and intensity of dreams shift. Early in the night, slow-wave sleep dominates, with less vivid dreaming. As REM periods lengthen toward morning, dreams become longer, more elaborate, and often more emotionally charged. This dynamic pattern highlights the brain's continuous balancing act, restoring, processing, and preparing the mind for waking life. Upon waking, the vividness of dreams can fade quickly, slipping through the grasp of conscious memory like mist. Yet their influence lingers beneath the surface, shaping mood, insight, and sometimes inspiration. Artists, scientists, and thinkers throughout history have credited dreams with breakthroughs and revelations, underscoring the creative power embedded in this nightly neuronal dialogue. Right now, as you rest, your neurons are crafting dreams, silent, shimmering, ephemeral stories that dance just beyond waking awareness. They whisper the secrets of your mind, bringing to life the unspoken, the hidden, the imagined. Dreams are often described as stories, vivid, sometimes surreal narratives that unfold in the silent theater of sleep. But beneath the surface of these nightly tales lies a deeper truth. Dreams are the brain's way of weaving together fragments of experience, emotion, and memory into intricate patterns of meaning. They are stories written not in words, but in the secret language of neuronal sparks. A language that translates the day's moments into the rich tapestries of the unconscious mind. When you close your eyes and drift into sleep, your brain enters stages of activity that are remarkably different from wakefulness. During REM sleep, the stage most closely associated with vivid dreaming, neurons fire rapidly in complex, sometimes chaotic patterns. This burst of activity arises in areas involved in emotion, memory, and sensory processing, while regions responsible for logical reasoning and self-awareness become less active. This unique neural landscape allows the brain to construct dreams, immersive worlds where time bends, logic loosens, and sensations blur. But where do these stories come from? The answer lies in the way the brain replays and recombines memories. Throughout the day, your experiences are encoded in networks of neurons across various brain regions. The hippocampus acts as a central organizer, linking sensory details, emotional context, and spatial information into cohesive representations. During sleep, the hippocampus and cortex engage in a delicate dance, replaying sequences of neuronal firing that reflect waking experiences. This replay helps consolidate memories, transferring them from short-term storage to long-term networks. Yet the brain does more than just replay memories during dreams. It reshuffles them. Bits and pieces of past events, emotions, and knowledge are woven together into novel combinations, creating new scenarios that have never been consciously experienced. A familiar face might appear in an unfamiliar place. A forgotten fear might be confronted in symbolic form. Distant memories might merge with current worries. This creative recombination allows the brain to explore possibilities, solve problems, and process emotions in a safe, simulated environment. The emotional centers of the brain, such as the amygdala and limbic system, are highly active during dreaming, imbuing these stories with feeling. This is why dreams often carry intense emotional weight, sometimes more vivid than waking life. The activation of these areas may help the brain regulate mood and process unresolved emotional conflicts, contributing to psychological resilience. Dreams are also sensory experiences. Neurons in the visual cortex generate images. Auditory areas create sounds and voices. Somatosensory regions evoke sensations of touch, movement, or pain. Although disconnected from the outside world, the brain creates rich, multisensory scenes that feel immediate and real. This sensory immersion is why dreams can be so captivating, strange, and memorable. Moreover, the diminished activity of the prefrontal cortex, the seat of executive function and critical thinking, during REM sleep reduces logical constraints, allowing dreams to be fantastical, illogical, and symbolic. This freedom from waking rules enables the mind to explore abstract ideas and emotions without censorship, often leading to profound insights or creative inspiration. The narratives of dreams often lack coherence or clear beginnings and endings, reflecting the fluid and dynamic nature of the underlying neuronal activity. They can shift abruptly, blend scenes, or circle themes in loops, mirroring the brain's ongoing internal dialogue. Dreams serve important functions beyond mere storytelling. They contribute to memory consolidation by strengthening neural connections and integrating new information with existing knowledge. They aid emotional processing by replaying and reframing experiences, helping to resolve conflicts and reduce stress. They foster creativity by allowing the brain to experiment with novel ideas and associations. And they prepare the mind for future challenges by simulating potential scenarios. Even though dreams may fade upon waking, their impact lingers. They influence mood, cognition, and behavior, subtly shaping how you perceive and respond to the world. Right now, as you rest, your brain is composing these silent stories, weaving the day's whispers into the nocturnal narratives of your mind. Each neuron, firing in rhythm, adds a brushstroke to this canvas, crafting dreams that are at once mysterious, meaningful, and deeply personal. Deep within the vast network of your brain, moments of silence hold profound significance. These are not empty voids, but purposeful pauses, intervals where neuronal activity dims, rhythms slow, and the mind retreats into stillness. This mysterious silence is as vital to your consciousness as the sparks of electrical activity that define thought and sensation. It is in these quiet moments that your brain finds balance, heals, and prepares to create anew. Neurons are often imagined as frenetic messengers, firing rapidly in endless streams. Yet, the brain is far more nuanced. It constantly shifts between states of excitation and inhibition, between bursts of activity and waves of calm. These silent interludes allow networks to reset, signals to be refined, and systems to coordinate effectively. Without such rest, the brain would be overwhelmed by noise, unable to filter important information or maintain focus. One of the clearest examples of this silence occurs during sleep, particularly in slow-wave sleep. In this stage, large populations of neurons synchronize their firing into slow oscillations, periods of collective silence punctuated by brief bursts of activity. This rhythmic pattern is thought to be essential for memory consolidation, synaptic homeostasis, and cellular repair. The quiet phases help prune unnecessary connections, conserve energy, and stabilize the neural architecture. Beyond sleep, silence also permeates waking brain function. Resting state networks, observed when the mind is not focused on specific tasks, exhibit characteristic patterns of low activity interspersed with spontaneous bursts. These quiet moments are believed to support self-reflection, creativity, and the integration of internal thoughts. The brain's default mode network, active during such rest, orchestrates this internal dialogue, allowing the mind to wander and consolidate experience. Silence in the brain also serves as a critical filter. Sensory input floods the nervous system continuously, but only a fraction reaches conscious awareness. Inhibitory interneurons play a key role here, selectively suppressing irrelevant or redundant signals. This gating function creates pockets of silence that sharpen perception and attention. Without these quiet windows, your mind would be drowned in constant stimulation, unable to focus or prioritize. On a cellular level, silence involves complex biochemical mechanisms. Neurotransmitters like GABA promote inhibitory signals, dampening neuronal firing. Ion channels regulate membrane potentials to stabilize resting states. Glial cells contribute by maintaining the extracellular environment, removing excess neurotransmitters and modulating synaptic activity. Together, these elements craft the pauses essential for healthy brain function. Moreover, silence is intimately linked to mental health. Disruptions in inhibitory signaling and the balance between excitation and inhibition are associated with disorders such as anxiety, depression, schizophrenia, and epilepsy. In these conditions, the brain's silence is compromised, leading to excessive noise, disorganized thought, or seizures. Restoring this balance through medication, therapy, or lifestyle can improve symptoms and enhance cognitive clarity. Silence also facilitates creativity and insight. Moments of quiet reflection allow the brain to reorganize information, forge new connections, and access subconscious knowledge. Many artists, scientists, and thinkers credit solitude and silence with unlocking their deepest inspiration. The brain's pauses are fertile ground where ideas incubate and evolve. Physiologically, silence conserves energy. The brain is an energy-intensive organ, consuming about 20% of the body's calories. Periods of reduced activity help manage this demand, allowing resources to be allocated efficiently. Cellular repair processes, protein synthesis, and metabolic waste clearance often occur during these restful states, supporting neuronal health and longevity. Even as you rest quietly now, your brain is embracing these moments of silence. Neuronal firing slows, networks synchronize into calm rhythms, and your mind softens its edges. This internal stillness is not emptiness, but a vital pause, a breath between thoughts, a space for healing, a foundation for renewal. In the dance of your mind, silence is the rhythm that holds the melody together. It shapes your capacity to think, feel, remember, and imagine. It is the quiet companion of every spark, the unseen presence that allows your inner world to unfold with clarity and grace. Within the intricate web of your brain, neurons fire in countless patterns, creating the very essence of who you are. But what does it truly mean when we say you? The question touches the deepest mystery of consciousness and identity. How do these tiny cells, devoid of awareness on their own, combine to produce the singular experience of self? The answer lies in the extraordinary way neurons work together, weaving a complex tapestry that defines you, your thoughts, memories, emotions, and sense of being. Each neuron is a simple messenger capable of receiving and sending signals, but incapable of conscious thought. It listens to the neurons around it, responds to chemical and electrical cues, and fires when the moment is right. Yet, on its own, a neuron is just a small, isolated spark. The magic happens when billions of these sparks ignite in patterns, synchronized and orchestrated, forming networks that encode information across space and time. These networks create the brain's internal map of the world, not just the outside world of sights, sounds, and sensations, but the inner world of feelings, desires, and memories. This map is dynamic, constantly updated by experience, shaped by attention and emotion. The sense of self arises from this ongoing interplay, from the patterns of activity that link sensory input, bodily states, and autobiographical memory. One critical player in this process is the default mode network, DMN, a set of interconnected brain regions active when the mind is at rest or engaged in self-referential thought. The DMN is involved in reflecting on the past, imagining the future, understanding others, and forming a coherent narrative of the self. It integrates information from diverse areas, allowing you to maintain a continuous sense of identity, despite the ever-changing flow of experience. Neurons within these networks communicate not just by firing in isolation, but through synchronized oscillations, rhythmic patterns of electrical activity that coordinate timing across distant brain regions. This synchronization allows distributed networks to act as unified wholes, binding disparate sensory and cognitive elements into coherent perceptions and thoughts. It is through this collective harmony that a unified sense of self emerges. Your personality, beliefs, values, and memories are all encoded in the patterns of connectivity among neurons. Repeated experiences strengthen certain pathways, making particular thoughts and behaviors more likely to arise. Habits, preferences, and even your style of thinking become etched into the brain's architecture. The you that you recognize is both a product and a reflection of this vast neural network. Moreover, the brain constantly monitors and integrates signals from the body. Interoceptive information about heartbeat, breathing, hunger, and emotion, grounding your sense of self in physical sensation. This embodied awareness ties your identity to the living organism, linking mind and body in a seamless whole. The brain's representation of the self is thus multidimensional, encompassing mind, body, and environment. Yet, the sense of self is also fluid and adaptable. It can shift with new experiences, altered states of consciousness, or even brain injury. Meditation, psychotherapy, and transformative life events can change how the self is experienced, revealing its constructed nature. Neuroscientific research shows that the self is not a fixed entity, but a dynamic process, continually recreated by the brain's ongoing activity. Disruptions to these neural patterns can alter or fragment the sense of self, as seen in conditions such as dissociative disorders, schizophrenia, or certain neurological diseases. These conditions highlight how crucial coherent neuronal communication is to maintaining a stable identity. When networks lose synchronization or connections falter, the unified experience of I can become confused or lost. Your consciousness, your personal narrative, your awareness of being, all depend on the harmonious firing of neurons across vast networks. Each thought you have about yourself, each memory of your life, each feeling of presence is encoded in this silent electrical dance. Your brain does not house a single self-neuron. Rather, you arise from the collective activity of countless neurons working together. Even as you read these words, neurons across your brain are coordinating, interpreting, and weaving the patterns that make this experience uniquely yours. The you observing these ideas is the emergent property of this immense, dynamic system. In the grand conversation of your mind, every neuron plays a part in telling the story of who you are. A story written not in ink, but in pulses of electricity and waves of chemistry, ever changing yet enduring. You are not just a collection of cells. You are the language they speak, the harmony they create, the consciousness they birth. And within this dance of neurons lies the deepest truth. You are the most extraordinary pattern of all. Within the vast and dynamic network of your brain, billions of neurons engage in a ceaseless, intricate conversation. Among the many forces shaping this conversation is one that often goes unnoticed, yet plays a crucial role in determining how information flows: inhibition. Inhibitory neurons and the inhibitory signals they send act as the brain's regulators, the quiet moderators who decide when to slow down, pause, or silence activity. This balance between excitation and inhibition is essential for healthy brain function, shaping everything from perception and thought to emotion and behavior. Imagine your brain as a sprawling city with countless intersections and pathways. Excitatory neurons are like the green lights, encouraging traffic to flow, while inhibitory neurons serve as red lights and stop signs, ensuring order and preventing collisions. Without inhibition, the brain would be overwhelmed by runaway excitation, leading to chaotic, uncontrolled activity. Too much inhibition, however, would stifle communication, resulting in sluggishness, disconnection, and reduced cognitive function. The delicate dance between these forces is what allows your brain to operate smoothly. Inhibitory neurons release neurotransmitters such as GABA, gamma-aminobutyric acid, which bind to receptors on target neurons and reduce their likelihood of firing. This process lowers the electrical potential within the neuron, effectively applying a brake to its activity. The strength and timing of inhibition are finely tuned, allowing for precise control over when and where signals propagate. This inhibition serves multiple critical functions. One is sharpening sensory perception. Inhibitory circuits help filter out irrelevant or distracting stimuli, enhancing contrast and clarity. For example, when you focus on a single voice in a noisy room, inhibitory neurons suppress competing sounds, enabling you to concentrate. This filtering is essential for attention, allowing the brain to prioritize relevant information while ignoring noise. Inhibition also supports temporal precision in neural firing. Many cognitive processes rely on the precise timing of neuronal activity, oscillations, and rhythms that coordinate communication across brain regions. Inhibitory interneurons help synchronize these rhythms by controlling when excitatory neurons fire, ensuring coordinated patterns necessary for functions such as working memory, language processing, and decision-making. Moreover, inhibition maintains the stability of neural networks. By preventing excessive excitation, it protects against seizures and other forms of neural hyperactivity. Disorders of inhibition can lead to epilepsy, anxiety, schizophrenia, and other neuropsychiatric conditions, highlighting its fundamental importance. Inhibitory neurons come in diverse types, each specialized for different roles and target areas. Some provide widespread inhibition, regulating overall network excitability, while others focus on specific microcircuits or cell types. This diversity allows the brain to implement complex, context-dependent control over information flow. Beyond regulation, inhibition contributes to the brain's capacity for plasticity and learning. By selectively silencing certain pathways, inhibitory circuits enable the formation of new connections and the refinement of existing ones. This gating mechanism supports the brain's ability to adapt, filter experience, and sculpt its own structure. During sleep, inhibitory signaling shifts to facilitate different brain states. In deep sleep, enhanced inhibition promotes the slow-wave oscillations critical for memory consolidation and neural repair. During REM sleep, modulation of inhibitory circuits allows for the characteristic brain activity underlying vivid dreams. The balance between excitation and inhibition is not fixed. It adapts to experience, development, and context. In early development, inhibitory circuits mature later than excitatory ones, shaping critical periods of plasticity. Throughout life, changes in inhibition reflect learning, stress, aging, and disease. Even at this moment, as you read and reflect, inhibitory neurons are at work behind the scenes. They refine your perceptions, focus your attention, regulate your emotions, and maintain the harmony of your inner world. Without their quiet but essential influence, the symphony of your mind would become a cacophony. In the grand dialogue of neurons, inhibition is the voice of restraint and wisdom, the signal that says when to pause, when to listen, and when to let go. It is the guardian of balance, the sculptor of thought, and the foundation of mental clarity. And within this balance lies the secret of your mind's power, a harmony born not just of sparks, but of silence. The brain is a master of rhythms, an intricate orchestra where neurons fire in synchronized patterns that rise and fall like waves upon the sea. These rhythms, known as brain waves, are the invisible currents that carry information, shape consciousness, and orchestrate the vast symphony of mental life. Understanding these brain waves reveals a profound language of timing and coordination, a secret code by which your neurons communicate and create your experience. Brainwaves are measured in frequencies, expressed in hertz, cycles per second, and classified into distinct bands: delta, theta, alpha, beta, and gamma. Each frequency band corresponds to different states of consciousness, cognitive processes, and neural functions, reflecting the brain's dynamic balance between excitation and inhibition. At the slowest end of the spectrum are delta waves, typically between 0.5 and 4 Hz. These deep rhythmic oscillations dominate during the deepest stages of non-REM sleep, a time critical for physical restoration and memory consolidation. Delta waves synchronize widespread neuronal populations, promoting cellular repair and synaptic pruning. They create the profound silence that allows the brain to reset and heal, laying the foundation for waking vitality. Theta waves, ranging from 4 to 8 Hz, often emerge during light sleep, drowsiness, meditation, and creative states. These waves are associated with memory encoding, emotional processing, and the transition between waking and sleeping. Theta rhythms facilitate communication between the hippocampus and cortex, supporting learning and the integration of new experiences. Their slow, rolling pattern mirrors the gentle waves of insight and imagination that arise when the mind relaxes. Alpha waves in the 8 to 12 Hz range are prominent during relaxed wakefulness, especially with closed eyes and restful alertness. They represent a calm, reflective state where the brain is internally focused, filtering out irrelevant external stimuli. Alpha oscillations help regulate attention, inhibit distractions, and prepare the brain for sensory processing. They act as a bridge between unconscious and conscious states, creating a quiet readiness for incoming information. Beta waves, spanning 12 to 30 Hz, mark active, engaged thinking, focused attention, problem solving, and motor control. These faster rhythms reflect heightened neuronal activity, supporting decision-making, planning, and execution. Beta oscillations are prevalent during cognitive tasks, conversation, and goal-directed behavior, enabling rapid communication among brain regions involved in complex processing. At the highest frequencies lie gamma waves, above 30 Hz, often reaching 40 to 100 Hz or more. Gamma oscillations are linked to conscious perception, sensory binding, working memory, and the integration of information across distant brain areas. They are thought to play a key role in creating the unified experience of consciousness by synchronizing neural activity at the millisecond scale. Gamma rhythms enable the brain to combine disparate sensory inputs into coherent objects, thoughts, and feelings. These brainwaves do not operate in isolation, but interact in a dynamic hierarchy. Slower waves modulate the amplitude and timing of faster ones, creating nested patterns of oscillations that coordinate local and global neural networks. This cross-frequency coupling allows the brain to balance stability and flexibility, combining focused processing with broad integration. Brainwaves are generated by the rhythmic opening and closing of ion channels in neuronal membranes, the interplay between excitatory and inhibitory neurons, and the architecture of neural circuits. Structures such as the thalamus play a pivotal role in pacing these oscillations, acting as a relay station and pacemaker that synchronizes cortical activity. The pattern of brainwaves shifts fluidly with behavior, mood, and state of consciousness. Meditation and relaxation increase alpha and theta activity, promoting calm and insight. Stress and anxiety elevate beta rhythms, correlating with heightened alertness, but also potential over-arousal. Deep sleep restores delta dominance, while focused attention amplifies beta and gamma frequencies. Disruptions in brainwave patterns are linked to various neurological and psychiatric conditions. Excessive slow-wave activity may be associated with cognitive decline, while abnormal beta or gamma oscillations relate to schizophrenia, epilepsy, and attention disorders. Therapies such as neurofeedback aim to normalize these rhythms, harnessing the brain's plasticity to improve function and well-being. Even now, as you rest, your brain waves ebb and flow, gently coordinating the silent conversation of neurons. These rhythms create the foundation upon which thoughts arise, memories form, and consciousness flows. The language of brain waves is the rhythm of your mind, the beat that holds your awareness together, the pulse beneath every feeling, every thought, every breath. And in this rhythm, your neurons dance, speaking softly, moving gracefully, alive in the endless song of life itself. Amid the countless neurons firing across your brain, a special class of cells quietly supports, protects, and shapes their activity. These are the glial cells, often overshadowed by the more famous neurons, yet absolutely essential for the brain's health and function. Far from being mere glue that holds neural tissue together, glia are dynamic, intelligent participants in the brain's secret language, influencing everything from communication to metabolism, repair, and plasticity. Glial cells come in several types, each with distinct roles. Astrocytes, the most abundant, are star-shaped cells that cradle synapses, regulate blood flow, and maintain the delicate chemical environment neurons require. They help control neurotransmitter levels by absorbing excess chemicals like glutamate and GABA, preventing toxicity and fine-tuning synaptic signaling. Astrocytes also supply neurons with energy substrates, converting glucose into lactate, which neurons use for fuel during high activity. This metabolic support is vital for sustaining the rapid firing that underlies thought and sensation. Another key glial type, oligodendrocytes, insulate neuronal axons with myelin, a fatty sheath that speeds electrical impulses by enabling saltatory conduction. Myelination not only accelerates communication, but also ensures signal fidelity, reducing noise and energy consumption. The integrity of myelin is critical for proper brain function. Damage to it underlies debilitating diseases like multiple sclerosis. Oligodendrocytes thus serve as both protectors and enhancers of neuronal signaling, shaping the efficiency of the brain's secret language. Microglia are the brain's resident immune cells, constantly surveying the environment for signs of injury or infection. They act as sentinels, clearing debris, pruning excess synapses during development and plasticity, and modulating inflammation. Microglia respond dynamically to changes, shifting from resting surveillance to active defense, releasing signaling molecules that influence neuronal survival and function. Their role links brain health to immune processes, highlighting the brain's vulnerability and resilience. Beyond these specialized roles, glial cells participate directly in synaptic communication. Emerging research shows that astrocytes can release gliotransmitters, chemicals that modulate synaptic strength and plasticity. They form tripartite synapses together with pre- and postsynaptic neurons, integrating signals and influencing neural networks in subtle but powerful ways. This challenges the traditional neuron-centric view, positioning glia as active partners in the brain's dialogue. Glial cells also contribute to the blood-brain barrier, regulating the passage of substances between blood and brain tissue. This selective gatekeeping preserves the brain's stable environment, protecting it from toxins and fluctuations that could disrupt delicate neuronal function. The dynamic interactions between neurons and glia underlie learning, memory, and adaptation. During synaptic plasticity, glial cells help remodel synapses, influence neurotransmitter uptake, and release factors that promote growth and repair. They respond to neuronal activity with changes in shape, gene expression, and signaling, highlighting a reciprocal relationship crucial for cognition. When the brain is injured, glial cells spring into action. Astrocytes form scar tissue to contain damage. Oligodendrocytes attempt to remyelinate axons, and microglia clear dead cells and debris. This coordinated response aids recovery, but can also contribute to inflammation and chronic conditions if unregulated. Understanding glial roles in pathology offers hope for novel therapies in neurodegenerative diseases, trauma, and mental health disorders. Throughout life, glia adapt to the brain's changing needs. Their numbers and activity fluctuate with development, experience, and aging. In young brains, glial cells support rapid growth and synaptic pruning, shaping circuits that underlie behavior and cognition. In aging, glial function may decline or become dysregulated, contributing to cognitive decline and vulnerability to disease. Even in the resting brain, glial cells maintain homeostasis. They regulate extracellular ion concentrations, recycle neurotransmitters, and support the slow rhythms of neuronal firing that define states of consciousness and sleep. Right now, as you sit quietly or drift toward rest, glial cells are at work behind the scenes, nourishing neurons, fine-tuning synapses, and preserving the delicate balance that allows your mind to think, feel, and be. They are the unseen caretakers of the brain's secret language, the silent partners in every thought, every memory, every breath. Without their steady presence, the symphony of neurons could not play. Within the vast and shadowy networks of the brain lies a remarkable feature that quietly orchestrates much of our mental life: the intricate communication between neurons, that shapes thought, perception, and behavior. This communication is far from random. It is a carefully choreographed dance where signals are not just sent, but finely modulated, timed, and integrated. At the heart of this dance are neural circuits, dynamic ensembles of neurons that work together to process information, generate responses, and create the rich tapestry of consciousness. Neural circuits are collections of interconnected neurons linked by synapses, forming pathways that carry electrical and chemical signals throughout the brain. Each circuit can be thought of as a specialized processor designed to perform particular functions, from simple reflexes that protect the body to complex networks that underlie reasoning, memory, and emotion. These circuits operate on multiple scales, from small local groups coordinating motor control to large distributed networks integrating sensory input with cognition. The architecture of neural circuits is remarkably diverse. Some circuits are feed-forward, transmitting information in a linear pathway from input to output. Others are recurrent, with loops that allow feedback and sustained activity, supporting working memory and decision-making. Inhibitory and excitatory neurons interact within these circuits to regulate activity, ensuring signals are balanced, precise, and meaningful. This balance prevents runaway excitation that could lead to seizures while maintaining the brain's flexibility and responsiveness. One fundamental type of neural circuit is the sensory processing pathway. When sensory receptors detect stimuli, light, sound, touch, the signals travel through dedicated circuits that filter, amplify, and interpret the input. These circuits perform rapid computations, extracting features such as edges in vision or pitch in audition, and relaying information to higher cortical areas where meaning is constructed. The fidelity and efficiency of these circuits determine how accurately we perceive the world. Motor circuits translate brain commands into coordinated movement. Within the spinal cord and brainstem, neuronal networks integrate sensory feedback and generate rhythmic patterns essential for walking, breathing, and other vital functions. Higher motor areas in the cortex plan and refine voluntary movements, communicating through descending pathways that modulate these lower circuits. Damage to motor circuits can result in paralysis or loss of coordination, illustrating their critical role. Memory and learning depend heavily on the plasticity of neural circuits. Experience modifies synaptic strengths within circuits, enabling the encoding of information and the formation of lasting memories. The hippocampus is a key hub where circuits link sensory and contextual information, facilitating the consolidation of memories. Distributed cortical circuits store different aspects of experience, dynamically interacting during recall and decision-making. Emotional processing involves circuits connecting the amygdala, prefrontal cortex, hippocampus, and other regions. These networks assess the significance of stimuli, generate effective responses, and regulate behavior. Dysfunctions in emotional circuits are implicated in mood disorders, anxiety, and PTSD, highlighting the importance of circuit integrity for mental health. Neural circuits are also the substrate of consciousness. Large-scale networks, such as the default mode network and attentional networks, coordinate activity across distant brain areas, enabling the integration of information necessary for awareness and self-reflection. Oscillatory synchronization within and between circuits supports this coordination, binding disparate elements into coherent perceptual and cognitive experiences. Importantly, neural circuits are not static. They exhibit remarkable plasticity throughout life. Synaptic connections within circuits strengthen or weaken based on activity, experience, and learning. New neurons may integrate into existing circuits, and dendritic structures remodel in response to environmental demands. This adaptability underpins the brain's resilience and capacity for change. During sleep, circuits engage in characteristic activity patterns that support memory consolidation and brain maintenance. Slow oscillations, sleep spindles, and sharp wave ripples reflect coordinated firing within circuits, replaying waking experiences and promoting synaptic homeostasis. These nocturnal patterns ensure circuits remain balanced and efficient. Disruptions to neural circuits can have profound effects. Traumatic injury, neurodegenerative disease, or developmental disorders can impair connectivity and function, leading to cognitive, sensory, or motor deficits. Understanding circuit dynamics is a central focus of neuroscience, with implications for therapies and brain-machine interfaces. At this moment, countless neural circuits in your brain are active, processing sensations, guiding thoughts, regulating emotions, and maintaining the ongoing narrative of your experience. They are the hidden architects of your inner world, the silent conductors of your mind's symphony. The brain's ability to regulate itself, to maintain a stable internal environment despite constant change, is one of its most remarkable features. This process, known as homeostasis, is essential for survival, cognition, and emotional balance. Within this self-regulating system, neurons play a central role, continuously adjusting their activity to respond to internal states and external demands. The homeostatic mechanisms of the brain ensure that neural circuits remain flexible yet stable, capable of learning and adaptation without becoming chaotic or fatigued. At the cellular level, neuronal homeostasis involves multiple interconnected processes. One key aspect is synaptic scaling, a form of plasticity that adjusts the strength of all synapses on a neuron up or down to stabilize firing rates. When a neuron experiences prolonged high activity, synaptic scaling reduces synaptic weights to prevent overexcitation. Conversely, after periods of low activity, synapses are strengthened to maintain responsiveness. This global adjustment preserves the relative balance of synaptic inputs while keeping overall activity within optimal bounds. Ion channel regulation also contributes to neuronal homeostasis. Neurons adjust the number and function of ion channels in their membranes, modulating excitability. By altering the flow of sodium, potassium, calcium, and chloride ions, neurons can fine-tune their threshold for firing action potentials. This ensures that neurons neither become hyperactive, risking excitotoxicity, nor hypoactive, leading to information loss. Homeostatic plasticity extends beyond individual neurons to entire circuits. Neural networks coordinate inhibitory and excitatory signals to maintain balanced activity across regions. Feedback loops involving neurotransmitters, neuromodulators, and glial cells help monitor and adjust network states. For example, inhibitory interneurons modulate excitatory neurons to prevent runaway activity, while astrocytes regulate extracellular neurotransmitter levels, contributing to synaptic stability. The balance between excitation and inhibition is critical for proper brain function. Disruptions can lead to neurological disorders such as epilepsy, autism spectrum disorder, schizophrenia, and depression. In epilepsy, excessive excitation overwhelms inhibitory controls, resulting in seizures. In contrast, imbalances in inhibitory signaling can impair sensory processing and cognitive flexibility in other conditions. Understanding homeostatic mechanisms offers insight into these pathologies and potential therapeutic avenues. Neuronal homeostasis also intersects with metabolic regulation. The brain consumes vast amounts of energy, and neurons must balance their activity with available metabolic resources. Energy supply, mitochondrial function, and glucose metabolism are tightly coupled with neuronal firing rates. Cellular stress responses detect metabolic imbalances, triggering adaptive changes to protect neurons and preserve function. Sleep is a vital component of brain homeostasis. During sleep, synaptic strength is globally downscaled, helping to reset neural circuits and conserve energy. This synaptic renormalization clears accumulated noise from waking activity, enhances signal-to-noise ratios, and supports memory consolidation. Sleep's restorative functions underscore the importance of homeostatic balance for cognitive health. Environmental factors influence neuronal homeostasis as well. Sensory deprivation, chronic stress, learning, and aging all impact homeostatic set points. For instance, prolonged sensory deprivation can lead to increased neuronal excitability as the brain compensates for reduced input. Chronic stress may alter neurotransmitter systems and receptor sensitivity, disrupting balance. Aging is associated with declines in homeostatic capacity, contributing to cognitive deficits and vulnerability to disease. At the systems level, homeostatic regulation involves interactions between the brain and the body. The hypothalamus plays a central role, integrating signals related to temperature, hunger, thirst, and circadian rhythms. Through autonomic and endocrine pathways, it modulates brain states and behavior to maintain overall physiological stability. This coordination ensures that neuronal homeostasis aligns with the body's needs. Even as you rest or engage with the world, your brain continually monitors and adjusts its internal environment. Neurons modulate their responsiveness, synapses recalibrate, and networks fine-tune their dynamics. This ongoing self-regulation enables you to learn, adapt, and maintain mental clarity amid a changing landscape of experience. In the grand complexity of the brain's communication networks, there exists a phenomenon that shapes not only how neurons talk to each other, but also how your mind processes information and responds to the world: neural synchronization. This is the process by which neurons fire together in coordinated rhythms, creating coherent patterns of activity that span regions, circuits, and even the entire brain. Synchronization is fundamental to cognition, perception, attention, and consciousness itself, acting as the invisible thread weaving the tapestry of your inner experience. Neurons generate electrical impulses, action potentials, that travel rapidly along axons and across synapses. However, for these signals to produce meaningful outcomes, timing matters. When groups of neurons fire in synchrony, their combined signals amplify, enhancing communication efficacy and enabling the brain to bind disparate pieces of information into unified percepts. This temporal alignment, often observed as brainwaves or oscillations, is a key mechanism for integrating sensory input, memory, and decision-making. Synchronization occurs at multiple scales. Locally, small networks of neurons can coordinate their firing to encode specific features, such as the edges of a visual object or the frequency of a sound. These microcircuits generate oscillations at various frequencies, allowing precise timing that enhances synaptic plasticity and information processing. The interplay of excitatory and inhibitory neurons shapes these rhythms, balancing excitation and restraint to produce stable patterns. On a larger scale, synchronization links distant brain regions, facilitating communication across the cortex and subcortical structures. Long-range coherence between areas such as the prefrontal cortex, hippocampus, and sensory cortices supports complex cognitive functions, including working memory, attention switching, and problem solving. This large-scale coordination often involves phase coupling, where oscillations in separate regions align their peaks and troughs, enabling efficient signal transfer. Different frequency bands correspond to distinct cognitive processes and states. Gamma oscillations, 30 to 100 Hz, are associated with feature binding and conscious awareness, allowing neurons representing different aspects of an object or concept to fire together, creating unified perception. Beta rhythms, 12 to 30 Hz, relate to active concentration and motor control, while alpha waves, 8 to 12 Hz, facilitate relaxed wakefulness and inhibitory gating of irrelevant stimuli. Theta, 4-8 Hz, and delta, 0.5 to 4 Hz, oscillations support memory encoding and deep sleep processes, respectively. Cross-frequency coupling, where slower rhythms modulate faster ones, creates a hierarchical organization that integrates neural activity across scales. Synchronization is not merely a passive phenomenon. It is dynamically regulated by neuromodulators such as dopamine, acetylcholine, and serotonin. These chemicals influence the excitability of neurons and the strength of synaptic connections, thereby shaping oscillatory patterns. Changes in attention, arousal, and emotional state modulate synchronization, adapting brain function to internal and external demands. Disruptions in neural synchronization are implicated in various neurological and psychiatric disorders. In schizophrenia, altered gamma oscillations correlate with cognitive deficits and hallucinations. In epilepsy, excessive synchronization leads to seizures. Autism spectrum disorders may involve atypical synchronization patterns affecting sensory integration and social cognition. Understanding these abnormalities offers pathways for therapeutic intervention, including neurofeedback and brain stimulation techniques. Synchronization also underlies plasticity and learning. Spike timing-dependent plasticity, STDP, depends on precise timing of neuronal firing. Synchronized inputs strengthen synapses more effectively, embedding information into neural circuits. During sleep, coordinated oscillations facilitate memory consolidation by replaying and integrating experiences. At this moment, as you engage with these words or rest quietly, neural synchronization orchestrates your thoughts, perceptions, and feelings. Groups of neurons align their activity, binding sensory details into coherent concepts, enabling focus and reflection. This invisible harmony allows your mind to function as a unified whole, rather than a collection of isolated signals. Neural synchronization is the rhythm of your consciousness, the temporal dance that unites the brain's vast networks, the code that binds sensation, memory, and thought into one seamless experience. The brain is an extraordinary organ, capable of generating the rich tapestry of human experience, from the vivid sensations of sight and sound to the subtle workings of thought and emotion. Central to this complexity is the remarkable phenomenon of brain plasticity, a dynamic process by which the brain constantly reshapes itself in response to experience, learning, and injury. This capacity for change underlies our ability to adapt, grow, and recover, making the brain a living, evolving system rather than a static organ. At the heart of plasticity lies the concept that neural connections are not fixed. Synapses, the junctions where neurons communicate, can strengthen or weaken over time. New connections can form, and others can be pruned away. This synaptic remodeling is driven by patterns of activity. Neurons that fire together tend to wire together, a principle known as Hebbian plasticity. Through this mechanism, experiences leave physical traces in the brain's circuitry, encoding memories, skills, and behaviors. Plasticity occurs at multiple levels. On a microscopic scale, individual synapses adjust their strength through long-term potentiation, LTP, or long-term depression, LTD. These changes alter the efficiency of signal transmission, shaping how information flows through circuits. At a larger scale, dendritic spines, tiny protrusions on neurons where synapses form, can grow or retract, modifying the architecture of neural networks. Even entire brain regions can reorganize in response to injury or sensory loss, a testament to the brain's adaptability. Learning new skills, from language to musical instruments, involves plastic changes in specialized brain areas. For example, practicing a motor task strengthens connections in the motor cortex and cerebellum, refining coordination and precision. Similarly, acquiring a new language engages plasticity in auditory and language-related regions, enhancing phonetic discrimination and grammar processing. This adaptability is most pronounced during sensitive developmental periods, but continues throughout life, albeit with varying degrees. Plasticity is also crucial for recovery after brain injury. When neurons are damaged, surviving circuits can compensate by forming new connections or reallocating functions. Rehabilitation therapies harness this capacity, encouraging use-dependent plasticity through repetitive practice and sensory stimulation. Understanding the mechanisms of plasticity has driven advances in neurorehabilitation, brain-computer interfaces, and potential treatments for neurodegenerative diseases. The balance of excitation and inhibition within neural circuits influences plasticity. Proper regulation ensures that synaptic changes are specific and controlled, preventing excessive or maladaptive rewiring. Neuromodulators such as dopamine and acetylcholine play pivotal roles in gating plasticity, linking it to motivation, attention, and emotional significance. Experiences charged with meaning or reward are more likely to induce lasting changes. Environmental factors profoundly affect plasticity. Enriched environments, social interaction, physical exercise, and cognitive challenges promote synaptic growth and resilience. Conversely, stress, isolation, and sensory deprivation can impair plastic mechanisms, leading to cognitive deficits. These findings underscore the importance of lifestyle and experience in shaping brain health. Plasticity is not without limits. Excessive or aberrant plasticity can contribute to disorders such as epilepsy, chronic pain, or addiction, where maladaptive circuits become entrenched. Conversely, aging and some diseases reduce plastic potential, making learning and recovery more difficult. Research into enhancing plasticity through pharmacological agents, brain stimulation, or behavioral interventions is an active and promising field. Even as you read these words, your brain is engaged in plastic processes, strengthening connections that support comprehension, forming new associations, and refining networks that underlie attention and memory. This continuous remodeling is the foundation of your ongoing growth, adaptation, and individuality. Brain plasticity is the essence of your mind's vitality. The ever-changing landscape where experience sculpts thought, where challenge births growth, and where resilience finds its home. Within the complex workings of the brain, timing is everything. The precise sequencing of neuronal firing, the when and how neurons communicate, is fundamental to how information is encoded, processed, and understood. This temporal aspect of neural activity is at the core of a fascinating mechanism called spike timing dependent plasticity, or STDP. STDP is a form of synaptic plasticity that depends not just on whether neurons fire, but on the exact timing of their spikes relative to one another. This timing-dependent learning rule enables the brain to adapt with remarkable specificity, refining connections based on experience and shaping cognition with exquisite precision. At its essence, STDP reflects the principle that neurons that fire together wire together, but with a crucial twist. It's not merely simultaneous firing that strengthens synapses, but the order and timing between spikes that determines whether a connection is potentiated or depressed. When a presynaptic neuron fires just before a postsynaptic neuron, within a window of milliseconds, the synapse is strengthened, making future transmission more likely. This causal sequence signals that the presynaptic neuron's activity may have contributed to the postsynaptic neuron's firing, reinforcing the connection. Conversely, if the presynaptic neuron fires shortly after the postsynaptic neuron, the synapse is weakened. This reverse timing suggests that the presynaptic neuron's firing is less relevant to the postsynaptic response, prompting a reduction in synaptic strength. This bidirectional modulation allows the brain to fine-tune connectivity, enhancing pathways that convey predictive or meaningful information while pruning less useful ones. STDP operates through complex molecular mechanisms. The precise timing of spikes influences calcium influx through NMDA receptors and voltage-gated channels, triggering intracellular signaling cascades that regulate the insertion or removal of neurotransmitter receptors at synapses. These changes alter synaptic efficacy, modifying how strongly neurons influence each other. The temporal sensitivity of these processes underlies the brain's remarkable capacity to encode temporal sequences, causal relationships, and patterns essential for learning and memory. This timing-dependent plasticity is fundamental in various brain regions. In the hippocampus, STDP contributes to spatial learning and episodic memory by reinforcing sequences of neuronal activity that represent navigational paths or event chains. In the sensory cortex, it sharpens feature detection and perceptual learning, refining the representation of stimuli based on experience. In motor circuits, STDP shapes the timing of muscle activation, enabling smooth, coordinated movements. STDP also supports the development and refinement of neural circuits during critical periods. Early in life, experience-driven, timing-dependent plasticity sculpts connections, establishing functional maps and sensory representations. Disruptions in STDP mechanisms during development may contribute to neurodevelopmental disorders, emphasizing its importance for healthy brain maturation. Moreover, STDP integrates with other forms of plasticity, such as homeostatic scaling and neuromodulation, creating a rich landscape of adaptive mechanisms. Neuromodulators like dopamine can gate STDP, linking plastic changes to reward and motivation, thus embedding learning within behavioral context. The timing rules of STDP enable the brain to encode not just static associations, but dynamic sequences and causality, supporting complex behaviors like language, music perception, and decision-making. This temporal coding is essential for predicting future events, understanding cause and effect, and navigating a world in constant flux. Even as you engage with this information, your brain's neurons are firing in precise temporal patterns. The timing of these spikes shapes synapses, reinforcing pathways that support your understanding, attention, and memory. Your ongoing experiences continuously refine these networks, sculpting the architecture of your mind. The brain is an extraordinary organ that relies not only on its cellular components, but also on a remarkable network of support cells known as glia. For a long time, these cells were thought to play merely a passive role, acting as glue to hold neurons together. However, modern neuroscience has unveiled their critical and active involvement in the brain's function, communication, and health. Glial cells are indispensable partners in the secret language of neurons, facilitating communication, maintaining homeostasis, and even influencing cognition and behavior. There are several types of glial cells, each with distinct roles that contribute to the brain's complex environment. Astrocytes, star-shaped cells that envelop synapses, are among the most abundant. They regulate the chemical composition of the extracellular space, maintaining optimal conditions for neuronal signaling. By clearing excess neurotransmitters like glutamate and potassium ions, astrocytes prevent excitotoxicity and help modulate synaptic transmission. Their processes also interact with blood vessels, linking neuronal activity to local blood flow, a relationship fundamental to brain energy supply and the basis of functional brain imaging. Oligodendrocytes provide another crucial service by producing myelin, the fatty insulating sheath that wraps around axons. Myelination dramatically increases the speed and efficiency of electrical signal conduction, enabling rapid and precise communication between neurons. This insulation is vital for coordinating complex functions, such as motor control and cognitive processing. Damage to myelin, as seen in multiple sclerosis, disrupts these signals, leading to neurological deficits, underscoring the importance of oligodendrocytes in brain health. Microglia serve as the brain's resident immune cells, constantly surveying their environment for signs of injury, infection, or abnormal activity. They respond to damage by clearing debris, releasing signaling molecules, and coordinating inflammatory responses. Beyond their defensive role, microglia are active participants in brain development and plasticity. They prune excess synapses during critical periods, shaping neural circuits and influencing learning. Dysregulation of microglial activity has been implicated in neurodegenerative diseases psychiatric disorders, and aging, highlighting their influence on brain function. Recent research has revealed that glia communicate not only with neurons, but also among themselves through calcium signaling and release of gliotransmitters, such as ATP and D-serine. These interactions modulate synaptic activity, plasticity, and network dynamics, contributing to the brain's information processing capabilities. Astrocytes in particular form tripartite synapses, together with pre- and postsynaptic neurons, integrating and regulating synaptic transmission in a sophisticated manner. Glial cells also play a role in maintaining the blood-brain barrier, a selective interface that protects the brain from harmful substances while allowing nutrient exchange. By regulating this barrier and controlling cerebral blood flow, glia help sustain the delicate balance necessary for optimal neuronal function. Throughout life, glia contribute to the brain's adaptability. They respond to changes in neuronal activity, participate in repair mechanisms following injury, and influence neurogenesis. Their plasticity and responsiveness are integral to learning, memory, and recovery. Despite their critical functions, glial cells often remain in the background, overshadowed by the dramatic firing of neurons. Yet, without glia, neurons would lack the support, protection, and modulation necessary to form the complex networks underlying thought, sensation, and behavior. At this very moment, as your neurons fire and your thoughts flow, glial cells are diligently maintaining the environment, fine-tuning synaptic transmission, and supporting the energetic demands of your brain's activity. They are the silent caretakers, the nurturing framework upon which your mind depends. Deep within the intricate labyrinth of the brain, a remarkable process unfolds silently, shaping every thought, sensation, and emotion you experience. This process is called synaptic plasticity, the brain's ability to modify the strength and efficacy of connections between neurons, known as synapses. Synaptic plasticity is the cellular foundation of learning, memory, and adaptation, enabling your brain to respond dynamically to the world and continuously rewire itself based on experience. At the heart of synaptic plasticity lies the concept that not all synapses are equal or fixed. Their strength fluctuates with use, activity patterns, and molecular signaling. When a synapse is repeatedly activated, it often becomes stronger, a phenomenon called long-term potentiation, LTP. Conversely, when activity decreases, synapses may weaken through long-term depression, LTD. These bidirectional changes allow neural circuits to fine-tune their responses, prioritize important information, and discard irrelevant signals, optimizing brain function. The molecular mechanisms underlying synaptic plasticity are complex and multifaceted. Key players include neurotransmitter receptors such as NMDA and AMPA-glutamate receptors, calcium ions, and a cascade of intracellular signaling pathways. Activation of NMDA receptors during coincident pre- and postsynaptic firing leads to calcium influx, which triggers biochemical events that strengthen the synapse by increasing AMPA receptor insertion or altering receptor properties. Conversely, different calcium dynamics can induce weakening of synapses. These processes adjust synaptic efficacy with remarkable precision. Synaptic plasticity is not uniform throughout the brain. It varies by region, synapse type, and developmental stage. The hippocampus, a critical area for memory formation, exhibits robust plasticity that supports spatial learning and episodic memory. The cortex also demonstrates plastic changes that underlie sensory processing, motor learning, and higher cognitive functions. Even in adulthood, plasticity persists, enabling lifelong learning and recovery from injury. Experience and behavior profoundly influence synaptic plasticity. Learning new skills, forming memories, and engaging in complex tasks induce activity-dependent changes in synapses. Environmental enrichment, social interaction, and physical exercise promote synaptic growth and efficacy, enhancing cognitive abilities. Conversely, stress, aging, and neurodegenerative diseases can impair plasticity, contributing to cognitive decline and mental health disorders. Sleep plays a vital role in synaptic plasticity. During sleep, particularly slow wave and REM phases, synaptic connections are selectively strengthened or weakened to consolidate learning and maintain homeostasis. This process helps prevent synaptic saturation and ensures efficient information storage. Disruptions in synaptic plasticity mechanisms are implicated in various neurological and psychiatric conditions, including Alzheimer's disease, autism spectrum disorder, schizophrenia, and depression. Understanding and targeting these processes offer promising avenues for therapeutic interventions. Beyond learning and memory, synaptic plasticity underpins the brain's remarkable adaptability, enabling recovery from injury and environmental challenges. It allows the nervous system to reconfigure circuits, compensate for lost functions, and maintain optimal performance. In this very moment, as your brain processes information, forms new thoughts, or recalls memories, synaptic plasticity is at work, adjusting the strength of countless connections, shaping your unique patterns of neural activity. It is the molecular dance that sculpts the architecture of your mind, crafting the endless symphony of experience. Deep within the intricate networks of the brain lies a shadowy aspect of the self, a realm often unacknowledged, yet profoundly influential on our thoughts, feelings, and actions. This is the domain of the shadow self, a concept first articulated by the pioneering psychologist Carl Gustav Jung. The shadow represents the unconscious parts of the personality, the thoughts, impulses, and desires that we repress, deny, or fail to recognize. Though hidden, the shadow wields significant power, shaping behavior in ways we may not fully understand or control. The shadow arises naturally from the human psyche's structure. As individuals develop a conscious identity, certain traits and experiences are marginalized because they conflict with the image we want to project or with societal norms. These rejected parts do not vanish. Instead, they retreat into the unconscious, forming a reservoir of potential energies, emotions, and motivations that lie beneath awareness. This unconscious content can be both destructive and creative. The shadow contains impulses such as anger, jealousy, selfishness, and fear, which, if unintegrated, may lead to projection, where we attribute these unwanted qualities onto others, causing misunderstandings, conflict, and emotional turmoil. It can also harbor talents, desires, and strengths that remain untapped until consciously embraced. Jung emphasized that acknowledging and integrating the shadow is essential for psychological wholeness and individuation, the process of becoming a complete, authentic self. Confronting the shadow involves bringing these hidden elements into conscious awareness, recognizing them without judgment, and understanding their origins and functions. This integration transforms the shadow from a source of conflict into a wellspring of personal growth and creativity. The shadow self manifests in various ways: sudden emotional outbursts, recurring dreams, irrational fears, or repetitive destructive patterns. It often appears through projections onto others, where we see traits in people that actually reflect disowned parts of ourselves. Relationships can become mirrors, revealing the shadow's influence, providing opportunities for self-discovery and healing. Therapeutic practices inspired by Jungian psychology, such as dream analysis, active imagination, and shadow work, facilitate engagement with these unconscious contents. By exploring dreams and symbols, individuals can access the shadow's messages and begin the process of conscious integration. This journey requires courage and honesty, as the shadow often confronts us with uncomfortable truths about ourselves. The shadow's role extends beyond the individual to collective and cultural dimensions. Societies project collective shadows, manifesting as social prejudices, conflicts, and systemic injustices. Recognizing collective shadows is vital for social transformation and empathy, fostering understanding across divides. Neuroscientifically, the shadow corresponds to implicit memory, automatic emotional responses, and subcortical brain activity that operate outside conscious awareness but influence behavior. These unconscious processes are deeply embedded in neural circuits, shaped by early experiences and ongoing interactions. Integrating the shadow leads to increased self-awareness, emotional balance, and authenticity. It frees energy previously consumed by repression and denial, enabling richer relationships, creative expression, and spiritual growth. The shadow, once feared, becomes a trusted companion on the path to self-realization. At this moment, as you reflect inwardly, unseen aspects of your shadow self may stir. Feelings, thoughts, or impulses previously unnoticed. Engaging with these parts with openness allows deeper understanding and integration, moving toward wholeness. In the vast and mysterious landscape of the mind, there lies a phenomenon that bridges the conscious and unconscious, shaping not only how we perceive the world, but also how we relate to ourselves and others. This phenomenon is known as the default mode network, or DMN, a complex network of interconnected brain regions that becomes active when the mind is at rest, engaged in introspection, daydreaming, or self-referential thought. The DMN is the neural substrate of our inner narrative, the silent storyteller that weaves together memory, identity, and imagination. Discovered through neuroimaging studies, the DMN includes key areas such as the medial prefrontal cortex, posterior cingulate cortex, precuneus, and parts of the lateral parietal cortex. These regions work in concert to generate a continuous stream of mental activity independent of external tasks or stimuli. When the brain is not focused on the outside world, such as during rest or passive wakefulness, the DMN lights up, reflecting the mind's tendency to wander inward. The functions of the DMN are diverse and deeply intertwined with our sense of self. It supports autobiographical memory, allowing us to recall personal past experiences and construct coherent life stories. This narrative continuity helps maintain identity over time, anchoring the fleeting moments of consciousness into a meaningful whole. The DMN also underlies theory of mind, the ability to attribute mental states to others, facilitating empathy, social cognition, and complex interpersonal understanding. Moreover, the DMN engages in prospective thinking, enabling us to imagine future scenarios, plan actions, and simulate possibilities. This mental time travel is essential for goal setting, problem solving, and creativity, providing a mental rehearsal space that prepares us for real-world challenges. The DMN's activity thus supports both reflection and anticipation, connecting past, present, and future in a seamless flow. Interestingly, the DMN exhibits a dynamic balance with task-positive networks, which activate during focused attention and goal-directed behavior. This push-pull relationship allows the brain to shift between internal mentation and external engagement, adapting to situational demands. Dysregulation of this balance has been implicated in various mental health conditions, including depression, anxiety, and schizophrenia, where excessive or diminished DMN activity can contribute to rumination, distractibility, or altered self-experience. On a cellular level, the DMN's activity reflects coordinated oscillations and synchronized firing across distant brain regions. This neural coherence facilitates efficient communication and integration of diverse information streams. The DMN's connectivity patterns are shaped by experience, development, and individual differences, contributing to personality traits and cognitive styles. The network is also sensitive to states of consciousness. During meditation, for instance, DMN activity often decreases, correlating with reduced self-referential thought and increased present moment awareness. This modulation links the DMN to mindfulness practices and spiritual experiences, highlighting its role in the fluidity of selfhood. Throughout life, the DMN matures and adapts. In children, its connectivity strengthens alongside developing cognitive and social abilities. In aging, changes in DMN function relate to memory decline and neurodegenerative processes, underscoring its importance for healthy brain aging. Even now, as you rest or ponder these words, your DMN is active, quietly weaving together memories, reflections, and imaginings, crafting the ongoing story of yourself. It is the neural stage upon which your inner life unfolds, the silent narrator shaping your sense of being. Our brain is a symphony of electrical and chemical activity, a vast network of neurons communicating through precise signals. But beyond these rapid-fire transmissions lies a deeper level of communication, a hidden code that governs how neurons influence each other over time, shaping not only immediate responses, but long-term patterns of connectivity and function. This secret language of neuronal signaling involves complex temporal dynamics, intricate feedback loops, and subtle biochemical conversations that together orchestrate the brain's remarkable capabilities. At the core of this language is the timing of neuronal spikes. Neurons communicate via action potentials, brief electrical pulses that travel along axons and trigger neurotransmitter release at synapses. But it's not just the presence of spikes that matters. Their timing relative to other neurons' activity encodes information crucial for learning and adaptation. This temporal coding allows the brain to detect causality, sequence events, and form associations, laying the groundwork for memory and cognition. One fundamental mechanism is spike timing dependent plasticity, STDP, where the precise order and interval between presynaptic and postsynaptic spikes determines whether synaptic strength is increased or decreased. This fine-tuned adjustment enables neurons to adapt their connectivity based on experience, reinforcing pathways that reliably predict outcomes while weakening less relevant connections. Through STDP, the brain continuously rewires itself, embedding the flow of time and causality into its very structure. Beyond STDP, neurons employ various firing patterns, bursts, rhythmic oscillations, and synchrony that modulate how signals propagate and influence target cells. Rhythmic activity in different frequency bands coordinates communication across brain regions, binding sensory inputs, memories, and motor commands into coherent wholes. The interplay of excitation and inhibition sculpts these rhythms, balancing precision and flexibility. Chemical signaling complements electrical impulses. Neurotransmitters and neuromodulators convey diverse messages, modulating synaptic efficacy, adjusting excitability, and shaping network dynamics. These molecules act over multiple timescales, from rapid synaptic transmission to slower, diffuse modulation, adding layers of complexity to neuronal dialogue. For instance, dopamine signals reward and motivation, gating plasticity and reinforcing behaviorally relevant patterns. Glial cells, once thought passive, actively participate in this secret language. Astrocytes release gliotransmitters, regulate neurotransmitter uptake, and influence synaptic strength, integrating into neuronal communication networks. Their involvement adds richness and adaptability to brain signaling, supporting homeostasis and plasticity. Feedback loops within circuits enable neurons to regulate their own activity and that of others, maintaining stability while permitting change. Recurrent connectivity supports persistent firing, essential for working memory and sustained attention. At the same time, inhibitory circuits provide critical checks, preventing runaway excitation and refining temporal patterns. The spatial arrangement of synapses and the properties of ion channels further shape signal propagation. Dendritic processing allows neurons to integrate inputs non-linearly, detecting coincident activity and generating complex responses. This dendritic computation expands the coding capacity of individual neurons, enriching the neural language. This secret language operates continuously, even during sleep and rest. Patterns of replay and reactivation consolidate memories, strengthen learning, and reset networks. Oscillations during different sleep stages coordinate these processes, reflecting an ongoing internal conversation vital for brain health. Disruptions in this intricate signaling can lead to cognitive deficits, psychiatric disorders, and neurodegenerative diseases. Understanding the nuances of neuronal communication holds promise for developing targeted interventions, enhancing brain function, and repairing damage. At this very moment, as your neurons fire and networks pulse, the secret language of your brain unfolds, silent, complex, and profoundly elegant. It is the code that shapes your thoughts, feelings, and actions, the dialogue through which your mind comes alive. The human brain is an astonishingly complex organ, capable of generating the rich tapestry of experiences, thoughts, and emotions that define our existence. But beyond its remarkable structural intricacy lies a profound mystery. How does the brain, through the collective activity of billions of neurons, create the unified experience of consciousness? This question touches the very core of what it means to be aware, to perceive, and to exist. Understanding the neuroscience of consciousness involves unraveling how neuronal networks integrate information, coordinate activity, and give rise to the seamless flow of subjective experience. Consciousness is not localized to a single brain region. Rather, it emerges from dynamic interactions across widespread neural circuits. Key areas implicated include the prefrontal cortex, responsible for higher-order cognition, the thalamus, which acts as a central relay station, and the posterior cortex, involved in sensory integration. These regions form networks that communicate through synchronized oscillations, binding together diverse sensory inputs and internal states into coherent awareness. A fundamental feature of conscious processing is the integration of information across time and space. Neurons fire in complex patterns, and through temporal synchronization, distant brain areas coordinate their activity. This neural coherence supports the formation of unified percepts, enabling the brain to merge visual, auditory, tactile, and emotional information into a singular experience. Without this integration, perception would be fragmented and disjointed. The global workspace theory proposes that consciousness arises when information is broadcast across a workspace in the brain, allowing various specialized modules to access and share it. This broadcasting is associated with widespread activation and synchronization, facilitating attention, working memory, and reportability. Such mechanisms enable the brain to prioritize relevant stimuli, form intentions, and guide behavior consciously. Another influential model, the integrated information theory, emphasizes the quantity and quality of integrated information as the basis of consciousness. According to this theory, the degree to which neural systems combine information into a unified whole determines the level of conscious experience. This approach offers a framework for quantifying consciousness and understanding its neural correlates. Consciousness also involves the distinction between self and other, subject and object. Neural circuits supporting self-awareness involve the default mode network and interoceptive processing, integrating internal bodily signals with external perception. This embodied self model provides a sense of agency and continuity, anchoring experience in a coherent I. Altered states of consciousness, such as sleep, anesthesia, meditation, or psychedelic experiences, reveal how changes in neural connectivity and dynamics affect awareness. For example, during deep sleep, reduced integration and thalamocortical connectivity correspond to diminished consciousness. Psychedelic states may increase global connectivity and reduce hierarchical constraints, leading to expanded or altered phenomenology. Recent advances in neuroimaging, electrophysiology, and computational modeling have begun to map the neural signatures of consciousness. Techniques like functional MRI, EEG, and magnetoencephalography reveal patterns of activation and synchrony correlated with conscious perception, attention, and cognitive control. Understanding these signatures aids clinical assessment of consciousness in disorders such as coma or vegetative states. Despite progress, the hard problem of consciousness, how subjective experience arises from physical processes, remains elusive. Neuroscience continues to explore the neural basis of qualia, the personal qualities of experience, seeking bridges between objective measurement and subjective reality. At this moment, as you engage with these ideas, your brain's networks are actively weaving the fabric of your conscious awareness. Through intricate coordination of electrical and chemical signals, your mind emerges as a living, perceiving entity, aware, reflective, and alive. Within the vast expanse of the brain's neural landscape, one of the most profound and essential phenomena is the generation and flow of emotions. Emotions are not fleeting whims, but complex, embodied experiences that shape perception, guide behavior, and color the fabric of consciousness. The neuroscience of emotions reveals how intricate networks of neurons, neurotransmitters, and brain regions collaborate to create the rich emotional life that influences every moment of human existence. At the core of emotional processing lies the limbic system, a collection of interconnected structures, including the amygdala, hippocampus, hypothalamus, and parts of the prefrontal cortex. The amygdala, often called the brain's emotional sentinel, plays a pivotal role in detecting salient stimuli, especially those related to threat and reward. It rapidly evaluates sensory input, triggering physiological and behavioral responses that prepare the body for action, whether fight, flight, or social engagement. The hippocampus contributes by providing context and memory, enabling emotions to be linked with past experiences. This linkage allows the brain to interpret situations based on learned significance, modulating responses accordingly. The hypothalamus orchestrates autonomic and endocrine outputs, translating emotional signals into changes in heart rate, hormone release, and other bodily states that underpin feeling. Higher cortical areas, particularly the prefrontal cortex, regulate emotional responses, integrating rational analysis with effective impulses. This regulatory function supports emotional awareness, empathy, and complex social behaviors. Through top-down control, the prefrontal cortex can modulate amygdala activity, tempering reactions and enabling adaptive responses. Emotions are communicated through a complex interplay of neurotransmitters and neuromodulators. Dopamine conveys reward and motivation, serotonin modulates mood and impulsivity, and norepinephrine triggers arousal and vigilance. Oxytocin and vasopressin influence social bonding and trust. These chemical messengers shape the intensity, duration, and quality of emotional experiences. Emotional processing involves dynamic neural oscillations and synchronization across networks, facilitating rapid communication and integration. Patterns of brainwave activity correlate with different emotional states, reflecting the ongoing dialogue between limbic, cortical, and autonomic systems. Beyond neural circuits, emotions are deeply embodied. Interoceptive signals from the body, such as heart rate, respiration, and visceral sensations, are integrated with brain activity to create the subjective feeling states associated with emotions. This bidirectional brain-body communication underscores the inseparability of emotion and physiology. Emotions serve critical adaptive functions. They prioritize attention, enhance memory encoding, motivate behavior, and facilitate social interaction. Positive emotions broaden cognitive scope and creativity, while negative emotions signal danger and promote caution. The balance and flexibility of emotional responses are essential for psychological health and resilience. Dysregulation of emotional circuits underlies many mental health disorders, including anxiety, depression, bipolar disorder, and PTSD. Understanding the neural mechanisms of emotion informs therapeutic approaches, from pharmacological treatments targeting neurotransmitter systems to cognitive behavioral therapies that reshape neural patterns. Developmentally, emotional circuits mature over time, influenced by genetic factors, experience, and environment. Early life experiences shape the sensitivity and connectivity of these networks, impacting emotional regulation across the lifespan. Even in restful moments, as you reflect or engage with these words, your brain's emotional systems are active, assessing, interpreting, and responding in subtle ways. This continuous emotional processing enriches your experience, providing depth, meaning, and motivation. Deep within the intricate network of the brain, a fascinating process unfolds that shapes how we understand ourselves, our surroundings, and our place in the world. This process is called self-awareness, the capacity to recognize oneself as a distinct entity with thoughts, feelings, and intentions. Self-awareness is not merely a philosophical abstraction, but a neurobiological phenomenon grounded in specific brain circuits and dynamic interactions among neurons. Exploring the neuroscience of self-awareness reveals how the brain constructs the experience of I, enabling reflection, empathy, and conscious control. Central to self-awareness is the integration of information across multiple brain regions. The prefrontal cortex, particularly its medial and dorsolateral areas, plays a pivotal role in higher-order cognitive functions that underlie self-reflection, decision-making, and metacognition, thinking about one's own thinking. This region supports the ability to evaluate oneself, consider alternative perspectives, and regulate behavior accordingly. The default mode network, DMN, a set of interconnected regions active during rest and internal thought, is closely linked with self-referential processing. It integrates autobiographical memory, future planning, and theory of mind. The understanding that others have minds and intentions different from one's own. The DMN's activity facilitates a coherent sense of identity over time, knitting together past experiences and future goals into a continuous narrative. Sensory and interoceptive inputs contribute to embodied self-awareness. The insular cortex processes internal bodily signals, such as heartbeat, respiration, and visceral sensations, grounding the sense of self in physical experience. The temporoparietal junction integrates multisensory information and is involved in perspective taking and distinguishing self from others. Damage or disruption in these areas can lead to altered self-perception or disorders like depersonalization, neural oscillations, and synchronization across brain networks facilitate the dynamic coordination required for self-awareness. Coherent activity patterns enable the brain to bind diverse sensory, emotional, and cognitive inputs into a unified experience of selfhood. Developmentally, self-awareness emerges gradually. Infants show early signs of bodily self-recognition, progressing toward more complex reflective capacities in childhood and adolescence. Social interaction, language acquisition, and cultural context shape this development, highlighting the interplay between neural maturation and experience. Altered states of consciousness, such as meditation, hypnosis, or psychedelic experiences, can modulate self-awareness, sometimes diminishing the sense of a bounded self and leading to feelings of unity or ego dissolution. These states offer insights into the neural substrates and flexibility of self-representation. Disruptions in self-awareness are evident in various psychiatric and neurological conditions. Schizophrenia, for instance, involves impairments in distinguishing internal thoughts from external reality, contributing to hallucinations and delusions. Autism spectrum disorders may feature differences in self-other processing affecting social cognition. Understanding the neuroscience of self-awareness informs therapeutic approaches, enhancing self-regulation, empathy, and psychological well-being. Techniques like mindfulness training engage brain networks associated with self-referential processing, promoting adaptive changes. Even now, as you read and reflect, your brain is actively constructing your sense of self, integrating memories, bodily sensations, thoughts, and emotions into the seamless experience of being you. In the ever-evolving landscape of the brain, there exists a remarkable capability that allows us to learn, adapt, and transform, the process of neuroplasticity. This extraordinary feature enables the brain to reorganize itself by forming new neural connections throughout life, responding dynamically to experiences, environments, and challenges. Understanding neuroplasticity unveils the profound potential of the brain to heal, grow, and redefine the very essence of who we are. At its core, neuroplasticity refers to the brain's ability to modify its structure and function in response to stimuli. This capacity is evident not only during early development, but persists well into adulthood, allowing lifelong learning and recovery from injury. Neurons, once thought to be static entities, are now known to be highly adaptable, capable of changing their connections, strength, and even generating new neurons in certain regions. Synaptic plasticity is the foundation of this adaptability. It involves strengthening or weakening the synapses, the communication points between neurons, based on activity patterns. Long-term potentiation, LTP, strengthens synapses through repeated stimulation, enhancing signal transmission and encoding learning and memory. Conversely, long-term depression, LTD, reduces synaptic strength, allowing for the pruning of less useful connections and maintaining balance within neural networks. Beyond synaptic changes, neuroplasticity encompasses structural alterations. Dendrites, the branching extensions of neurons, can grow new spines, increasing the number of synaptic contacts. Axons can sprout collateral branches to form new pathways. In some brain regions like the hippocampus, neurogenesis, the birth of new neurons, adds fresh cellular elements to the circuitry, contributing to plasticity and cognitive flexibility. Experience profoundly influences neuroplasticity. Environmental enrichment, physical exercise, social interactions, and cognitive challenges promote synaptic growth and neural remodeling. These factors enhance learning capacity, memory retention, and emotional resilience. Conversely, stress, trauma, and deprivation can impair plasticity, leading to cognitive deficits and mental health issues. Neuroplasticity also underpins recovery from brain injury. When areas are damaged by stroke or trauma, nearby neurons can adapt by forming new connections or taking over lost functions. Rehabilitation techniques leverage this plasticity through repetitive practice and sensory stimulation, encouraging functional reorganization and improving outcomes. Molecular mechanisms driving neuroplasticity involve complex signaling pathways triggered by calcium influx, neurotransmitter release, and gene expression changes. Neurotrophins, like brain-derived neurotrophic factor, BDNF, support neuron survival, growth, and synaptic modulation, acting as key facilitators of plasticity. The brain's plastic nature is evident in diverse phenomena: language acquisition, skill learning, habit formation, and adaptation to sensory changes like blindness or deafness. It enables the brain to compensate for lost senses or functions by reallocating resources and rewiring circuits. However, plasticity is a double-edged sword. Maladaptive plasticity can reinforce harmful behaviors or pathological patterns seen in addiction, chronic pain, and certain psychiatric disorders. Understanding the nuances of plastic changes is crucial for developing targeted interventions that promote beneficial rewiring while minimizing detrimental effects. Even now, as you engage with this narrative, your brain is actively reshaping itself, strengthening synapses, forging new connections, and pruning old ones, crafting the neural architecture that supports your unique thoughts, memories, and skills. The human brain is a marvel of evolutionary engineering, composed of billions of neurons interconnected in vast networks, each playing a role in generating the rich experience of life. Yet, within this complexity, there exists a vital balancing act that is crucial for maintaining mental health, clarity, and adaptability: the balance between excitation and inhibition. This delicate equilibrium ensures that neuronal activity remains neither chaotic nor excessively subdued, enabling the brain to function optimally in processing information, regulating emotions, and controlling behavior. Excitatory neurons use neurotransmitters such as glutamate to stimulate neighboring neurons, promoting the propagation of electrical signals across circuits. This excitation is essential for perception, learning, and movement, as it drives the transmission of information and the activation of downstream neurons. However, unchecked excitation can lead to excessive firing, noise, and instability, which could manifest as seizures, anxiety, or cognitive overload. Inhibitory neurons, on the other hand, release neurotransmitters like gamma-aminobutyric acid, GABA, that suppress neuronal firing, providing a braking mechanism. This inhibition is not simply a dampening force, but a sophisticated modulator that shapes timing, synchrony, and precision of neural responses. By selectively silencing certain pathways, inhibition sharpens signal-to-noise ratio, filters irrelevant inputs, and coordinates complex oscillations critical for cognition. The interplay between excitation and inhibition, EI balance, is dynamic and context-dependent. It varies across brain regions, developmental stages, and behavioral states. For example, during heightened attention or learning, excitation may transiently increase to enhance processing, while inhibition adapts to prevent overexcitement. During sleep, inhibitory mechanisms promote slow-wave oscillations that facilitate memory consolidation and brain recovery. Neural circuits maintain EI balance through intricate feedback loops and homeostatic plasticity. When excitation rises, inhibitory neurons adjust their output to restore equilibrium and vice versa. Disruptions to this balance can have profound consequences. Excessive excitation relative to inhibition is implicated in epilepsy, where runaway neuronal firing leads to seizures. Conversely, too much inhibition may contribute to cognitive rigidity or disorders such as schizophrenia and autism, where information processing and social cognition are affected. At the molecular level, EI balance is regulated by the expression and function of various receptors, ion channels, and neurotransmitter systems. Genetic and environmental factors influence these components, shaping individual susceptibility to neuropsychiatric conditions. Understanding these mechanisms provides avenues for targeted therapies aimed at restoring balance, such as GABAergic drugs, neuromodulation, and behavioral interventions. This balance also underpins the brain's oscillatory rhythms, the synchronized patterns of neural firing across frequencies like theta, alpha, beta, and gamma waves. These rhythms coordinate communication across distant brain regions, enabling complex functions such as attention, working memory, and conscious awareness. EI balance shapes the generation and modulation of these oscillations, highlighting its centrality in cognition. Developmentally, EI balance evolves from infancy through adulthood, influenced by sensory experience, learning, and plasticity. Early disruptions can alter critical periods of brain maturation, affecting lifelong cognitive and emotional outcomes. The adaptability of this balance throughout life underlines the brain's resilience and capacity for change. Even as you engage with these words, your brain is continuously tuning its excitation and inhibition, calibrating neural activity to maintain harmony. This silent, ongoing process is essential for your thoughts to be clear, your emotions regulated, and your actions purposeful. As we conclude this journey through the secret language of your neurons, remember that your brain is not a static organ, but a dynamic, ever-changing symphony of electrical and chemical signals. Every thought, emotion, and experience emerges from this extraordinary dance of connectivity and communication. Embrace the wonder of your mind's inner world, knowing that within you lies a universe of complexity, resilience, and endless potential crafted one neural whisper at a time.